The following is a presentation of the Six Arrows Radio Network.
Today on the Workbench, interfacing microcontrollers to the real world. Stay tuned. Welcome to the Workbench. I'm your host, George, KJ6VU.
And I'm Jeremy, KF7IJZ. Welcome to episode 15 of the Ham Radio 360 Workbench podcast. George, how you doing?
Hey, I'm doing great, Jeremy. How are you?
I am very well. If this is your first time joining us here at the Workbench, welcome in. Every other week, opposite of the Ham Radio 360 podcast, George and I get together to take a deep technical dive on various topics related to amateur radio and things associated with amateur radio.
That's right. And whether you're a real seasoned amateur radio operator or if you're just starting out, we want to bring you interesting technical topics from a broad range of ideas, from do-it-yourself and making projects to doing deep dives on technical topics all the way to operating your gear out in the real world.
This episode of The Workbench is sponsored by CADsoft. Get your free copy of Eagle PCB design software at www.cadsoft.io.
And Elecraft, the premier provider of high-performance transceivers like the K3S, the KX3, and their new super compact KX2.
And by MCM Electronics, where you can outfit your workbench with the tools, equipment, parts, and popular boards such as Arduino and Raspberry Pi. Save 10% with the code RAD10 through January 31st. That's RAD10 for 10% off your order.
So, Jeremy, what's new in the news world this evening?
Well, there's stuff all over the place. Probably one of the more interesting things that will be applicable to at least 300 of our listeners who have managed to get antenna analyzer boards is our friend Chris down at Rocket City 3D has completed the design for the Ham Radio 360 antenna analyzer case. And two ways to get this. Number one is he has made available for free the STL files. If you have access to a 3D printer, you're going to be able to print one yourself. And also, they have made available for sale a quality case printed in ABS, available in several different colors. And I'm actually kind of surprised how inexpensive it is.
How much are those?
They are $15, and that is shipped to you in the continental United States.
Oh, that's pretty reasonable.
It is reasonable. The only small caveat to this, of course, is that these cases are made on demand, so there may be a day or two lag when you order one. I know he had mentioned to me that he has already sold several of them, and I want to thank them again for, specifically Chris, for taking the time to basically get the kit and build the antenna analyzer, and then spend some time working on a model to hold it. And then making these available both for sale and for free, in the spirit of the fact this is an open source project. So, Chris, thank you guys very much. And again, a huge shout out to Rocket City 3D. You can find them online at rocketcity3delta.com. Or I guess I should say rocketcity3d.com, but ham have it.
Do you know, when you look at the case, have you seen one? Like, is it two pieces that screw together, or how does it work?
Yep, it is a top half and a bottom half, and then there are little inserts. There are holes on the top of the case, and there are little inserts that go in for the buttons.
Oh, okay. So you can take with all the stock normal components. You don't have to change anything. It just is designed to fit.
Yep, he designed to fit it, even with the fact that the little Arduino Micro overhangs the overall board just a little bit, which we promise next time we won't do that.
No, we won't. No. We won't do that. Well, that's awesome.
I'd like to point out I didn't do that.
Yeah,
I'm not smart enough to do that.
I did. It was my. Yeah. Okay. While we're on the antenna analyzer, I wanted to mention something on the firmware side. So Barrick K6BEZ, who's the designer of the original circuit and the developer of the original set of firmware, is now a official signed in user on the Ham Radio 360 forums. So he's going to start checking that out. So Barrick's been like super busy with life and work and other things, and he hasn't had a chance, but he called me up this week and said, hey, I really want to get more engaged and find out what's going on. And I said, well, the good news is that we haven't had a whole lot of complaints. So you should check out the forums, and there's an occasional question or two, and he's going to dive in there and provide some information and guidance, which is great.
That's actually really awesome, because we've had several of our listeners have pinged us about certain things from, we've had a couple of people say, hey, there's a good chance that this diode would actually work instead of the glass germanium ones. Actually had somebody this week send me a message and say this, I don't know, well, non-glass is a germanium diode that was a direct replacement for the one we were using. And of course, we haven't tried it to see if it works or not. I looked at the data sheet, and it doesn't mention anything about forward voltage drop, so I don't know if it would actually work. And then there are a couple of other diodes that and somebody else had suggested, which are actually made specifically to be used as detectors in RF circuits. And then on top of that, our community has actually been busy tinkering with the firmware.
Yeah, I've noticed there's several people have made some modifications, and at least one person did a complete rewrite of all of the code from scratch. So there's a lot of enhancements. And this is really like the whole idea of this was, one, to provide a useful piece of equipment for you and your station off the shelf, but of course, secondly, to get the experience building it. And third is, in a community project like this, you take what someone did as a good solid starting point, and then you could make derivatives. You could enhance the software, you could make suggestions on the hardware changes, build your own version, or maybe we do another spin of this at some point in the future with enhancements. But it's exactly this kind of community engagement that we really wanted to do. So it's really, really fun to see it. And part of the challenge with that is when you start out with a piece of code, for instance, and then now you've got 5 or 6 or 8 versions of that, which is the real version. And so to put some structure to this whole thing, one of the other fellows that we're working with, Derek, AG6PO, is helping us organize all this. So Derek is a professional in the software-defined radio world. So he's got a lot of software experience and hardware experience. So Derek set up our GitHub site, which is where we're going to put the main line of code and also official derivative versions. So the idea is that we want to be able to make it easy to share enhancements and new versions of software. The problem is, if somebody takes it, makes a mod, and sticks it back in there, and it hasn't been tested, the next guy comes along and takes it, and it may or may not work right. So we have to be careful to have officially released versions of firmware and other versions which are not officially supported. So we're going to be very clear about all that, and we'll be able to support multiple streams of the software on the GitHub repository, so you can find other people's versions. So we're also going to take that same officially released versions of the firmware as it improves and have links from the 360workbench.com website. So think about the GitHub as the big repository with potentially multiple versions of the software, and the website as the very simplified user interface where you just know, here's the one thing I need. So it makes it very easy to find it. So thanks to Derek for jumping in and managing the software delivery architecture for us. So that'll be great. And we'll use the same idea in future projects. Now,
out of curiosity, do we have any indication when we will get our next, like, quote unquote, official release with some of these newer features incorporated?
Derek is reviewing all of the modifications that people have been doing and posting. And so he's going to look at the different implementations and decide which one would be the official one or which modifications would be folded into it, and pick the best one. I was talking to him today about it, and he said that he may wind up with one official full release and maybe a simplified version, a light version, if you will, that maybe kind of stripped down, that might be easier for people to wrap their head around if they're just starting to learn, if they want to actually look at the source code. So we'll see where that goes, but it's up to Derek to manage the official release of what's the quote supported unquote version. And by the way, by supported, I mean we might answer a question, but the community will really support it. But it'd be like the reference version.
Well, I do want to thank our listeners, those of you who've taken it up, because honestly, what we shipped was very much minimum viable product. It did exactly what it was supposed to do and no more. And what was kind of cool is at solving some of these problems, right? Like being able to interrupt the sweep by pressing the band button to quickly get to the band you're looking for, things like that. Actually teach you quite a bit about interfacing controls with a microcontroller, because you have to learn about things like interrupts. And so, I mean, I didn't realize it at first, but when I sat down and started thinking about it, this actually was kind of a cool little problem solving about, like, you know, how can we make the experience better? But then you also learn quite a few techniques about developing for Arduinos along that, you know, that journey.
Well, yeah, and that's the whole idea behind making the source code available, because maybe the next thing you want to do is not an antenna analyzer. You want to build something totally different. But like you're saying, those basic ideas and code examples, you'll just take those and use those in your project and play with it. And what's kind of fun is when you release something like this, hopefully you have a group of smart people who are going to jump on it and make these kind of enhancements. And of course, you always sit back and think, well, why didn't you do that the first time? Wasn't it obvious? And usually there's so much work in getting the first generation of anything out the door. And there's always a big, long list of enhancements you'd like to make. And having a community to actually take it over and make those enhancements is great. So thanks very much, everybody, for really participating and, you know, building it and trying it out and adding new software features and whatnot. And big thanks to Barrick for his design and his support, and really to Derek for helping to organize all this madness.
Yes, thank you very much. So something that came across my radar, last week. I was listening to an episode of the Amp Hour that was recorded a week or two ago, and they referenced a project that was an open source lab bench supply, an open source lab power supply. And didn't think really much of it, but then our friend Gerald, JNU, sent me an email this week and showed me where the thing was available. And they are doing a crowdfunding project, but they're not using Kickstarter or Indiegogo. They're using something called Crowd Supply, which when I heard that title, I thought that was the actual domain for the power supply, right? Because it was like crowdfunded power supply. So if you go to crowdsupply.com, this is featured on the homepage. The power supply project is the Echo Echo Zulu Hotel 24005.
Well, it just rolls right off the tongue, doesn't it?
I don't understand why couldn't they have called it like the OSPS U1 or something? I don't know. But anyway, this power supply is actually it's pretty interesting. It doesn't seem to be a linear supply, but it seems to be a very quiet switcher with resolution for voltage and current down to 10 millivolts or 10 milliamps. Did you see what I just combined voltage and amps to create vamps?
Millivamps. I've never heard of a millivamp.
Millivamps, yeah. So, and then apparently it may actually be able to be a little bit more precise than that. But the 2 channels. And for 0 to 40 volts, unfortunately, it does not seem to do negative voltage, up to 5 amps per channel, for a maximum of 155 watts per channel. Both the channels can be bridged, put in a serial so you can extend your ranges. But $400 for a 2-channel computer controllable either via USB or Ethernet. There are a lot of features like remote sensing included. And you know what's the most interesting part about it?
What's that?
There are no knobs.
Oh, is it touchscreen?
It is a touchscreen, like a 3.2 or 3.5 inch LCD touchscreen. And to adjust values, you touch them and just kind of move your finger back and forth.
So if I go to the store to buy a bench supply and I'm just looking for a 0 to 20 volt 3 amp supply, that's like a Tenma thing, would probably be like $80 or $100?
Let's say up to $150.
Okay, so you said, how much is this thing?
This thing is $400.
Okay, so besides getting 2, so it'd be like twice-ish the price. So what's so cool about it?
First of all, it is run off of an Arduino Due, which is I don't remember what the actual microprocessor is on that board, but it's bigger than what's on an Uno, I believe. The design is 100% open source, so you get all the schematics, all the BOM, everything. You get the firmware on that runs the power supply itself, if you are a developer and there are applications that you want to develop for, they give you a lot of tools, including like a simulator that will simulate the power supply on your computer. It has, like I said, USB and Ethernet to be able to interface with it. And honestly, when I look at this, the first thing I actually had somebody ask me on Twitter, this is $400 compared to $400 for a Rigol. I think it's the DP832, which is a 3-channel supply. It has like a couple of known issues about, I think grounds are coupled when they shouldn't be or something. I apologize for not remembering correctly. It's not, I think it's maybe 3 amps per channel for 2 of them. And one of them is, I don't remember all the specs for it. But first of all, this power supply you have higher resolution for voltage and current metering. As far as all the control stuff, that's probably about the same. And of course, with a Rigol, you can spend another $400 or $500 to unlock features that would make it higher resolution and whatnot. But it's Rigol's design, it's Rigol's software. It's not open source. They have a DP711 for $300, which is a single channel, and I think it might be like 30 volts, 5 amps. I can't remember. But for $100 more, you get double the channels with this thing.
And is it all pre-assembled, or is it a kit?
So like any crowdfunding thing, they have everything from a $10 donation to, I think you can buy circuit boards, you can buy certain things like that. But for $400, yeah, it's fully assembled. So there are 40 days left in this campaign. This thing has been discussed quite a bit on the EEV blog forums, I believe, but it looks like a pretty cool project, and so I will make sure there is a link to it in the show notes. It's also, as far as I know, granted I haven't been looking, but it's one of the first examples of open source test equipment.
Yeah, interesting. Did Dave Jones have a opinion on this?
I don't remember. I don't think so. Cause like when I first heard it mentioned on the episode, he said he wasn't following it because, his forum gets 1,000 posts a day and he just doesn't have time. Plus he was getting ready to go on vacation.
Well, looking at the specs, you said 0 to 40 volts and 0 to 5 amps. I don't know what the Rigol is, but as variable power supplies go, that's a pretty broad range. Cause a lot of these, let's say the $80, $100 bench supply is not going to go to 40 volts and probably not 5 amps. It's probably 0 to 20 or 30 and maybe 0 to 3 amps. So this is a fair bit of capacity. So looks pretty good.
Yeah, and it's an open source project.
Very good. Are you going to get one?
I'm thinking about it because I was one of the things on my list for Dayton this year is I actually was really looking at the new DP711. I rarely need more than one channel. I've got 2 bench power supplies right now. I would like something that's actually a little bit more higher resolution and something that is lower noise. And for years, I've always wanted to buy an 832 at Dayton. And of course, until last year, they had never brought any. And then last year, they sold out of them in like the first 10 minutes. So I never got one. So I don't know. I am considering it. And if I do end up upgrading my bench power supply, I will probably give one of the ones on my bench away on the show.
Oh, nice.
Yeah.
Very nice.
So we'll see what happens. This is one of those things, right? My list of things I want to buy is far greater than my ability to buy them because there are still like 3 radios ahead of this.
Including the TH-74.
Yeah, there's still that. And then Hytera DMR radio. But honestly, the only thing that bothers me about it personally is that I like knobs. Like I really,
and this
I like
is all touchscreen.
It's all touchscreen. I like a good rotary encoder.
Yeah, who doesn't?
So, but still, cool project worth talking about.
Yeah, very cool. Very nice. What else you got?
I want to give a shout out to our friend Dan Romanchik, KB6NU. Dan has actually, he teaches tech in general classes, and I noticed today he has video recordings of his technician class available on his YouTube page, which I will link to. But I think it was either last weekend or the week before, he was going to do a live stream of a general class, and he's actually going to do that again tomorrow on YouTube. And of course, by the time this post, it'll be too late. But I highly recommend, if you're interested in attending one of these virtual classes, follow Dan on Twitter. His handle is at Kilo Bravo 6 November uniform. But I think that's really cool that he's giving back to the community by actually trying to host these virtual classes.
Oh, very nice. That's great. His books are I've heard they're quite good, actually. Have you looked through any of those?
Yes, I have the extra one, and I just haven't had the time to dedicate to it. And actually, if I remember correctly, he gives the technician one away for free on his website, which is kb6nu.com.
Oh, very good.
Yeah.
Yeah. We also have some Dayton update.
Yeah, so Dayton tickets are on sale, sort of.
What does that mean? It's sort of.
If you go to the Dayton Hamvention website, you can order tickets by mail. Online ordering is not yet available. There was a video posted by Tim Duffy from DX Engineering with one of the folks from the Darrow board, kind of talking about some of the things as far as they're getting ready. And he had mentioned in that video that the person who maintains their web stuff apparently had some family issues and hasn't been able to be engaged. And I have a feeling they're waiting to be able to go in and change the pricing or something, because he mentioned the tickets were going to be $22 pre-ordered, and that includes parking.
Mm-hmm. Not bad.
Yeah. And there'll be $27 day of. He mentioned that they're working to see what they can do to get high-speed internet out there. If somebody needs a phone line or a dedicated network drop, I guess they're working with AT&T to make that available. The food is supposed to be much better because they're working with professional catering companies and also looking at local food trucks, which there are some really good food trucks in Dayton. Mm-hmm. And then he tried to address people's concerns about the fact that there's a lot of parking and events going to be happening like in green spaces. And of course, everybody's like, well, it's just going to be a mud pit, but he really is pointing out the fact that these areas are designed specifically for what hams are going to use them for. I mean, these areas are used for a lot of events where people park on the grass and they have really good drainage and whatnot available. So it was nice to see a little bit of update. Of course, we still haven't gotten word as far as getting a booth yet, have we?
We have not. I've sent emails to the powers that be and asked for the information, and I'm getting absolutely no response. And the website says, stay tuned. So there's maps of the layouts, so you can look at where all the booths are, but there's no booth assignments. They're not taking orders yet, which is something they need to kind of get to pretty quick here.
Yeah, they mentioned they were talking about, and this has been talked about before, but I have a feeling they haven't figured out how much vendor space to make available yet, because obviously there's the facilities that are there as they are, but then they were talking about they've referenced before like these big white pop-up pavilions that are air conditioned and climate controlled, and kind of like they're effectively giant tents. But more structurally sound than just a tent. And they kind of reference that they're trying to decide, if they need those or how many they need. So, yes, I personally would love to know that we had Dayton locked up. But yeah, I'm remaining hopeful.
The vendor map, it shows some things, and now maybe this is preliminary, but the vendor map shows 4 buildings that have vendor booth spaces in it, and then 2 other spaces that have forums. The 4 buildings with vendor spaces seems like, and this is kind of a guess, seems like fewer spaces than at the old Hera Arena. So we'll see. There are 3 forum rooms, which is a small fraction compared to Hera. Hera, we had like 6, at least double this. So I don't know, how that's going to go, if they're just going to have half as many forums or what, but I guess that all remains to be seen. I think the new location is going to be nice. I'm excited to see what it's all about, but I wish we could get our booth nailed down. So actually, the thing I was going to mention earlier is we're all planning to be there. So Kale's planning to be there. Hopefully, he'll make it, and I'm planning to be there. And I hear you're going to be driving in from Ohio.
Yeah. It's quite a distance for me. It's a big sacrifice. I'm going to be in the car for a very long time, but yes, I am going to make the trek again this year to bring coverage to our listeners.
So it should be really good. I'm looking forward to it as usual. So I'm sure they'll get it all sorted out, and I'm sure it'll go great. But everybody's excited and antsy to figure out where we're going to be, if we're going to be behind the this livestock display, behind the goat rodeo amphitheater, or whatever they have there.
Well, yeah, I'm actually just very excited that it's new. I mean, Old Dayton was great, but there's it's nice to kind of see this hopefully take a big step forward. And I'm going to be honest, I don't expect everything to be perfect. And I know there will be problems and there will be people that will complain about them. But let's have some patience. Let's take an iterative mindset that we're going to try this. Whatever doesn't work out, we're going to learn, and we'll, inspect and adapt, and it will be better the next year. And I know that these folks are working their rear ends off to try to make everything as perfect as possible the first go around, but there's just some stuff they won't learn until the 20,000+ hams descend on Xenia, Ohio.
Yeah, my only piece of advice for anybody who wants to complain is next time you should volunteer to organize it. We'll see what you think about it. So
exactly.
Try putting one on yourself. So yeah, more power to them. So yeah, we're all quite excited.
So do you have any other news items?
I've got a few things, a few quick announcements. The first one is I want to say a big congratulations to our friend Curtis. Curtis is K5CLM, and he's the host of the Everything Ham Radio podcast. And the reason I wanted to shout out to Curtis is last week he passed episode number 50, the big 50. So Curtis is stuck to it for the last couple of years and puts out a really fun podcast on all kinds of stuff relevant to ham radio, and he did 50 episodes, and he's still going strong. So congratulations to Curtis. The other thing I wanted to mention is that I bought something new to build. Like I need another project. I hope it doesn't sit on the bench unbuilt forever, but I bought a QRP Labs Whisper transmitter. I guess it does Whisper and QRSS and some other modes, but it's a little transmitter kit, the one designed by Hans Summers. And I heard about it. We talked about this on the last episode on the QSO Today podcast with Eric 4Z1UG, which is a great series. You really should listen to his podcast. But anyway, he interviewed Hans Summers, and it was so interesting that I went ahead and bought the complete kit for the Whisper transmitter. So I'm really looking forward to building that and seeing how well that all works.
Yeah, I'm excited about hearing your experience with that, because I think I mentioned that on the last episode that it looked like a cool little kit, and it just neat to see what Flea Power does, especially with all of these modes that are really designed to be extremely weak signal. I think that'll be a fun little toy.
Well, and in particular for me, the Whisper aspect of it is very interesting. So for those of you who don't know, Whisper is the weak signal propagation reporter. And the idea is that you have a transmitter that sends a slow speed data signal, and it includes your call sign, your grid square locator, I think maybe your power output. And usually these transmitters are less than a watt. And then you can go to the whisper.net, I think it's whispernet.net or whatever website, and you can see a map of the world, and then you could filter out the signals that are being heard. So there's hundreds, if not thousands, of stations around the world that have receivers, and they're hooked to the internet. And any station that hears your transmission is logged in the database. So you can go to this website and say, show me my call sign, and it'll show you the 2 or 10 or 20 stations that received your signal and where they are geographically located. So the point of this was to be able to see right now what the HF propagation is on a particular band at this point in time and in what direction. So it's very cool. I'm really looking forward to building it. I guess I could have done it with a regular transmitter, but I wanted just a complete turnkey little box. And I also think we'll use it on field day. It'd be fun to fire it up and hit the go button on field day and see where we're transmitting to on 20 or 40 meters where we usually operate and see what happens.
Awesome. Yeah, and the other thing that's cool about it is you're only going to get about 200, 250 milliwatts out of it. And, most of our radios don't go down that low. So, like I said, I'm really excited about hearing your experience and also finding out what the receiver board is supposed to do, because that was the part that puzzled me.
Yeah, I did not get the receiver, so I just got the transmitter.
Okay.
So the first thing I want to do is just beacon and see what the propagation is, relying on everybody else's receiver. And then once I get rolling down that path, then I want to see what kind of receiver to set up. And I did some web searching for Whisper receivers, and there's a kind of a mishmash of different things with small SDRs and with dedicated receivers and so on. And I don't know what the best one is, but I figured I'd try the transmitter first and go from there.
Well, and like I said, they make a receiver board. I just don't know. It's a quadrature output into a sound card at a minimum, but somehow it made it sound like it would work with the rest of the components in this Whisper stack. Maybe we should actually reach out to Hans and ask him.
Yeah.
If only there were this thing called the internet.
Yeah, if only. What I really want, and I haven't looked around enough to find what I'm looking for yet. What I really want is a receiver and a Raspberry Pi so that I could just turn it on at home and just be on the network and not have to have a normal radio turned on. And I'm sure probably 8 guys have done this already. So, 8 different designs. So anyway, I'm going to be looking around for that. Maybe Hans already got one, so we'll see.
Awesome. So that's kind of a good tie-in to, let's give a shout out to Baycon.
Everybody loves Baycon.
That's newsy.
So Baycon's our Baynet Ham Radio Club annual conference. It's coming up in 2 weeks on the 28th of January. And we got a whole bunch of great presentations. We've got presentations on DXing and software development for ham radio stuff, building your own test equipment, microwave building and operating. And some guy's doing a presentation on LiFePO batteries. This guy, Jeremy.
That guy's an idiot. He doesn't know anything.
Well, he's got a YouTube channel. He looks pretty credible to me, but you never know.
Anybody can have a YouTube channel. That doesn't make them... No.
Right.
No, I'm excited to be a remote presenter. And of course, I told my mom that I was doing this because we were trying to maybe plan something that week. And I was like, no, I have to virtually speak at a conference. And my mom's like, oh, that's a big honor. And I was like, it's just some people in California. It's fine.
Well, it is a big honor.
It's a major award. No, I am super excited. I feel like I have no business being there because some of the people that are presenting are just infinitely smarter than I am, and I'm actually terrified that one day the amateur radio community is going to find out what a fraud I am. I realize seriously. So over the weekend, last weekend, I had a thought that crossed my mind is that if amateur radio were the wizarding world of Harry Potter, George, you would be a wizard and I would be a squib. So,
far from it. No, it's amateur radio, which means that we don't do it for a living and we do it because we love it. So you're perfectly qualified.
There we go. So, are you going to be is there going to be a way to capture some of these presentations? Or are you going to be doing interviews?
Good question. So the way we set it up, we're going to be recording every one of the presentations. So we've got the slides and we will have audio recordings. And then I've asked each one of the presenters if they would allow us to post the recording of their talk and their slides to the web. And some of them said absolutely, and some of them said I'd rather not because I may say something stupid. I didn't say that. I said that. But they said, well, I don't really, I don't know. And so everybody who said, well, I don't know if I want my audio posted, I asked them if they would be interviewed for the podcast, and every one of them said yes. So at a minimum, we will either record their presentation and post the PowerPoint, or we will do a separate live interview with them and make it part of a podcast episode. So all of the presenters will have content on. And if you want to find out who's presenting and what they're talking about, go to www.baycon.us. That's BAYCON.us. And you can see each presenter, their topic. And if you're in the Bay Area, come on by. It's free. We would shake you down for a donation when you come in. But if you're resistant to that, you can still come in and enjoy it. It'll be 9 to 5, Saturday the 28th in Sunnyvale, California, in the heart of Silicon Valley. In fact, the building that it's in, it's at the Plug and Play Tech Center. And Plug and Play is a technology incubator. So if you have a startup that you're trying to get off the ground, it's the kind of place where you and your 4 or 5 co-founders or slave labor coders can go and incubate your little company and hopefully turn it into something. And they provide services, and they're very kind and generous to offer us their big meeting room for free. And at this point, we've got over 100 people registered. I think we're at about 115 as of today. So it'll probably be about 130, 150 by the time the dust settles. So, and by the way, we have some shameless, way cool giveaways. So the big grand door prize for the event will be an ICOM ID51A Plus 2, the brand new D-Star handy talkie, which is $510 at the local radio store. ICOM generously donated that to us as a grand prize. So that's really cool. And since we have a big D-Star repeater, of course, that's great. And we got some other donations. We got a donation from Ham Radio Outlet, so big thanks to those guys. So Ham Radio Outlet in Sunnyvale, California, donated a Bio-NO battery and charger.
Sweet. So, well, that's actually convenient since I'm going to be specifically covering that battery in my presentation.
Yeah, exactly. So it's very timely. In fact, when I was over there talking to them and I said, what do you want to donate? And they said, how about a Bio-NO battery? And I said, well, that's perfect. Of course. We'd love that. So
awesome.
Yeah, they're quite generous.
Is ICOM going to be there this year?
No, it turns out they couldn't be there, but I talked to Ray Novak, who's the head sales guy for amateur and for the commercial business there. And Ray said, yeah, we can't make it this year, but we'd be happy to donate a radio and we'll send you a whole bunch of giveaways. So there's a bunch of other stuff they're going to send too. And it's very nice of them.
That is pretty awesome. No, I'm very much looking forward to presenting. I wish I could be there in person to attend. Of course, the other thing going on that weekend is if you can't attend BayCon, don't forget that is Winter Field Day, which my club has actually rented a cabin in an Ohio State park, and they are going to go up, and their goal is to get every bonus multiplier they can. Which
sounds like fun, but cold.
Yeah. Well, I don't know. It's supposed to be in the 50s and 60s next week here, so it might be, it might not be.
So, but speaking of Winter Field Day, I mentioned this to one of the guys who's running the talk-in station for BayCon, and I said, "Hey, by the way, and he's a big soda guy." I said, "Hey, Tim, it's a Winter Field Day weekend." Yeah, I know it is. I said, "Do you want to bring an HF radio?" And there's a huge patio off the main room at the event location. So I said, do you want to set up an HF station and run Winter Field Day? He said, sure. So we're going to have a station going at the same time.
Cool.
Yeah.
Well, George, what's on the workbench this week?
Oh, just, I guess the build project stuff. So the next build project we talked about last time, the low voltage disconnect. And so for you guys listening, I sent Jeremy a pile of circuit boards to the Midwest Division Destructive Testing Lab.
My basement.
I hope you have ventilation, buddy.
I have a door that opens to the outside and a fan.
Well, nothing smells better than burning traces on a circuit board, I'll tell you.
Well, okay, so go ahead and finish explaining what this is, and then I actually have a comment about that, because I realized something that was kind of silly recently about this.
So we've been talking about what to do as the next build project, and it takes a couple of months from the time you go, yeah, let's build that, till it's really ready to release. So while we're wrapping up the last batch of antenna analyzer boards, which, by the way, will arrive here on the 16th of January, and then I need to ship them to Kale. So we have another 150-odd circuit boards coming in to finish that off. Anyway, so the circuit is a DC power circuit that has a power pole in and a power pole out. And it senses the voltage, and if the voltage is above or below a certain level, then it opens the circuit, and if it's good, it closes the circuit, and that way it doesn't discharge your battery excessively. And another idea we had was to make a circuit that would allow you to have two power sources and one load. So you might have one power source as a power supply and another power source as your battery. And when the power supply is running, life is good. And when the power supply goes off because you lose AC power, the battery just keeps chugging along and provides power to the load. So the next version of this project board is going to be not only the low voltage disconnect, but also this circuit that lets you share two sources into that same load all on one board.
And with an Arduino on board, you can also do power monitoring, measurement of voltage, display how much current is going through, etc.
Yeah, exactly. So we'll have a ability to plug in an LCD display, and we'll also have the same Arduino Pro Micro that we used in the antenna analyzer will be on the board. So if you build the analyzer, you're kind of familiar with the Arduino and maybe even the code. And so when you start playing with the code on this one, it'll be the same tools, it'll be the same kind of code, just a different application.
You know, I want to set an expectation because already this thing has already gone through a couple of mutations as far as what it's going to be and, you know, what kind of value will it deliver as a project. You know, there's still, I'd say, a lot of prototyping. And like I said, you know, now that we've had a successful, community project, we wanted to just basically be very transparent about the development of this thing, So speaking of which, as far as what's on my bench right now is a U.S. Post Office first class mailing box. And inside of that box, I think you sent me, 7 boards? One thing I'll mention, though, that was really cool that I didn't know about is you had also sent me their Anderson power poles, but they're power poles, instead of having just like the crimp-on metal tabs, they're actually designed to be soldered to PCBs, which I had never seen before.
Yeah, there's something that you won't find at the normal radio supply store. So it's the standard power pole housing, but these pins are really big. They're very wide. They're about 0.2 of an inch wide, and they're a 90-degree angle. So you mount them with these tabs through the circuit board, and they'll handle, easily 45 amps or more. Not that this circuit will, but the connectors will more than adequately handle the current.
You know, and that's actually, so the reason that George mailed these things to me is if you have been on my YouTube channel, the last power and radio related video I did was actually a comparison of the BioNO lithium iron phosphate battery, which they had provided to me at my request, against a formerly A123, now I think it's NEC Power bought them, and then just like your garden variety 7 or 9 amp hour lead acid AGM battery. And so I have a device that is a programmable DC load, and I have this basically in order to be able to simulate loads on batteries. It's a pretty cool tool. There's a nice computer interface, so I can get all the data out of it. I can graph it, which when we do the Baycon presentation, I had done a lot of data analysis. I had shared this with George, and those are what are going to go into my slides, and we'll, make them available here. But what we want to make sure is that the thing is designed to actually safely handle the amount of current that you as a user could put through it. And right now there have been two the thing has been, designed firstly around a maximum of a 15 amp load. And then there is an option potentially for up to 30 amps. But of course, the key thing are the copper traces. And as we discussed, I think it was the last episode, in order to carry more current, more copper has to go on the board, and there's a point at which if you stick with thin copper, the traces get absolutely unusably wide. And as you increase the density of copper on the board, those traces can get smaller. So George took a wild guess in designing this. And what I'm going to do is I'm going to hook the board up to this DC load, and then I'm going to hook up, connect it to a power supply I have here, which is capable of providing up to 40 amps at 13.8 volts. And we're going to see at what sustained current does the board catch on fire.
That's why I wondered.
Literally.
You had ventilation.
Because that's the failure condition of an overcurrent printed circuit board is fire.
And the stage before fire, which is, wow, that's hot.
Yeah, and so what I realized is you sent me this big batch of boards, but it occurred to me I really only need one.
Well, I figured that, it's like doing fuse testing. You can't just have one. So, I would send you a bunch.
But the reason I say that is because I will start up with I mean, truthfully, 2 would have been good because the first I'll do is sustained current, where I will basically just slowly dial the current up and leave it running for maybe an hour or something. I really wish I had a thermal imager for this project because that would be really cool, but I don't. But I do have a good non-contact thermometer and that you can adjust the emissivity on. So I found the emissivity ratings or coefficient for bare copper. So I will strip away the mask over those traces so I can shoot the gun at it and get real temperatures. And I should be able to model pretty well, even running a 100-watt radio, say on, sideband, and I can simulate different duty, like really fast switching duty cycles to even simulate CW. So that should be fun. I'm probably going to get started on that sometime this week, and that'll help decide whether or not we're building a device for 100-watt barefoot devices or QRP.
or if we're building a low-voltage disconnect or a fuse.
Yeah. It's a low-voltage disconnect that is also a high-current disconnect, but it only works once,
it's
i.e. a fuse.
One-time programmable fuse. And by the way, the board that we have as prototype uses just 1 ounce copper, so it's the thinnest copper that you normally use only for low current applications, but the traces are pretty wide and there's very, very short traces. So I'm really curious to see at what point it does start to heat up, because what we may find is that because the length is so tiny that it really doesn't matter if you use a lightweight copper or not. That'd be a pleasant surprise. Or we could find that it does in fact fail at about the point where you would expect it to fail, even if it is very small. And we know we need to go to something larger. By default, if we were going to fabricate these boards today, I would go with the 3 ounce copper regardless. But who knows? We may find that the lighter weight copper is actually adequate. The other thing that we will try is to augment the copper with bus wire. So one of the ways that you can work around a problem like this is not to rely solely on the copper to carry the current. So I've got some tinned number, I think it's 14 or 18 gauge bus wire, and you could probably just solder the bus wire to the bottom of the board where the traces are, and it would handle all the current just fine. But it'd be nice if it's all handled in the circuit board material, and we'll see.
Yep. And as I test this, I should probably take a video too, and I can share it with our listeners. But no, it'll be fun once I get it set up and find a fire extinguisher.
Yeah, I would have that handy if I were you.
Yeah, I hate to say, it's not a joke. I am effectively going to be pushing these boards until the point that the copper just burns up. And I have had some experience with very high current sources burning copper traces up, and it literally happens in a flash.
Yeah, and it doesn't smell good.
No.
It's pretty bad. Well, so that's pretty exciting. I'm looking forward to that. And I also, by the way, while you're doing the destructive testing, I'm going to send off for version 2 of the board, which is larger than the one you've got there, that has the DC, whatever you want to call it, the DC power combining circuit on it that actually sits in series in front of the low voltage disconnect. So I'll probably get those boards sent off maybe this weekend and get some to start playing with those circuits.
So the combiner, I think it would probably be safe. Oh, yeah, actually, even that's not a good description. What I was going to say is calling it similar to like a 12-volt UPS, but really it is just a fast switcher that if one load fails, one source fails, it'll switch to the other. At this point, we have not looked at trying to put a charging circuit in it to kind of back charge the battery while it's, working off the normal 12-volt load. So could be a feature, maybe not, but something we are looking at. Now, we've talked about the antenna analyzer a lot. A lot of good stuff. You know what we owe our listeners?
Oh, I do.
Yeah, we promised for our faithful listeners that for our last 3 episodes, or last four, whatever, who made it to the very end of the episodes, we offered to give away antenna analyzer boards. And for the Thanksgiving show, if you had sent us an email that said turkey, you were eligible to be entered to win the board we were going to give away for that. One that said jingle bells and one that said ho, ho, ho. So we are going to give away 3 antenna analyzer boards tonight. Well,
now that was the promise. But
do we not have any left?
Well, I have a batch coming in on Monday. So
Are people okay?
Yeah, so we'll have boards, but we're not going to give away one analyzer board for each one of those contests.
Well, but we said we would.
Well, how about if we give away 3 instead?
What?
I mean, 3 for each contest.
So 9 boards total.
9 boards total.
Boom.
Yeah.
Ham Radio 360 magic right there.
Yeah, it took us a long time to figure that out. So we should run through the winners for each of these contests here.
All right, and so we will be reaching out to these winners via email. But for now, right now, we have call signs for most of you. There were a couple of you we don't. So I will start off with turkeys. Matt Chenoweth, Steve Swantz, and Martin Wintergren, Alpha 6-5 Delta Charlie, which is a cool call sign because it's from Dubai.
You know, when I saw that, I thought, oh, that must be a typo. What's Alpha 65? And I looked it up, and I'll be darned. He's got a whale of a station actually in Dubai. So I think Cale's going to have a slight coronary trying to figure out how to ship a circuit board to Dubai.
If I remember correctly, he gave us an address in the United States too. But
smart man.
Yeah. So again, Matt Chenoweth, Steve Swantz, and Martin Wintergren, Alpha 6-5 Delta Charlie, are the winners of the turkey boards.
Congratulations, guys. And the second batch, which was the Jingle Bells contest, went to the following 3 winners. The first is Brian, November 1, Foxtrot, India, Yankee. The second board goes to Francine, Alpha Foxtrot 7, Oscar Bravo. And the third board goes to Bill, Kilo Mike 6, Bravo, Yankee, Delta. So Brian, N1, FIY, Francine, AF70B, and Bill, KM6BYD.
Congratulations, Jingle Bells winners. And finally, on the Ho 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 list, we have Conrad, Kilo 6, Bravo, Whiskey Delta. We have Misha, Victor Echo 9, Golf India Sierra. And we have Daniel, Victor Echo 5, Delta Lima Delta.
Yay.
So
congratulations.
Thank you guys for listening to us all the way to the end. Thank you for taking the time to send us a note. And just to be clear, I mean, these emails literally went to our Ham Radio 360 emails. Like, this wasn't trying to build a list or anything. So you're not going to get spammed having sent this, except the winners will get notified via email that they have won. But thank you guys very much again for encouraging us. Thank you to our listeners for making this literally at this point 4.5 times as successful as we thought it would be. That's the cool thing. We can quantify the success by the number of boards that have been sold.
Yeah, thank you so much. And I got to say, when we look at the emails, when people would send us their turkey jingle bells or ho, 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 besides that, they always have a comment, and it could be something as simple as, hey, great show, or maybe a longer description of what they like about it, or maybe what they don't like about it. And we read, of course, every one of those 5 times over and take them to heart. And it's really very gratifying. So that's really kind of how we get our feedback. So thank you so much for that. We really appreciate you taking the time.
Thank you very much for the encouragement. So George, at this point, why don't we hop into the main show content this week, which is all about interfacing microcontrollers with the real world.
Okay, that sounds super. Let's do that, and we'll start in just a minute right after this. Elecraft is a premier provider of high-performance transceivers like the K3S and the portable KX3 and their new super portable compact KX2, which is my top pick as a portable HF rig today. It runs 10 watts, 80 through 10 meters, single sideband, CW, and data modes. It's a fantastic little radio, and you'll be amazed when you see what kind of performance you can get out of something this small. And a high-capacity internal battery lets you run the radio for several hours, whether you're on the trail, camping, or taking the radio anywhere portable. You'll really enjoy using this little rig. With an excellent reputation for product quality, innovative designs, and customer service, check out Elecraft at www.elecraft.com.
George, you and I had gotten to talking after the parts episode about some ideas for upcoming shows. And some of the work that you had been doing recently on upgrades to your repeater site got us to talking about a topic. And, we've talked about microcontrollers before, and we've talked about some generic projects. But one of the things I thought would be interesting was to actually start talking about how do you interface a microcontroller or even a single board computer with the physical world?
Yeah, it's a great topic because at the end of the day, a lot of the applications we can imagine as hams either measures something in the physical world or controls something in the physical world, and knowing how to go from that delicate little microcircuit of a microcontroller to that relay or whatever that thing is you're using is really basic necessary information.
What we're talking about is interfacing with microcontrollers like Arduinos or PICs. And of course, these days, there's a lot of other microcontrollers that are becoming popular, like the STM32 series, but also how to interface with things like a Raspberry Pi or a Beagle board. And the long and short of it is that the principles here are pretty much the same regardless of the architecture. The big difference is what you do in software, but there are still different types of signals, different ways of interfacing with these components, and I think we'll give a good overview today.
Yeah, and there's lots of things to kind of wrap your head around. And for some people listening, I'm sure you're going to listen to this and think, yeah, well, I know all that stuff, and we're going to cover turf that you're very familiar with, and hopefully there'll be something that you might learn out of that. But for a lot of people who've never built an electronic circuit with a microcontroller, this is kind of new. And there's some really very basic rules of the road that we can cover that will explain how you can easily interface to that physical world. So hopefully we'll cover that stuff and make it useful and give you some examples along the way.
All right, so where do we start?
Well, I think the first thing is to realize that there are many different kinds of physical interfaces on these kind of parts. So there's digital inputs and outputs and analog inputs, and there's digital serial communications channels of various kinds and other special purpose kind of interfaces. So we'll get to each one of those kind of in series. But I guess the first thing to talk about is the voltage levels that you're going to see on these devices. So the first thing you're going to want to look at for the component that you're using, the microcontroller, is what's the voltage. And typically today, there's really two voltages that are by far the most common. There's 5 volts and 3.3 volt interfaces. So, for example, a Raspberry Pi uses a maximum 3.3 volt interface voltage. An Arduino typically is 5 volts. A PIC microcontroller could be 3 or 5 volts. There are some Arduinos that are 3.3 volts. So what we're really talking about is the voltage that's supplied to the component, and that also dictates the maximum voltage on one of the interface pins. And to put this in some historical context, the 5 volts was really commonly started to be used 30 plus years ago, when logic gates were widely available in the 7400 series or TTL components. And those parts.
What does TTL stand for?
TTL stands for transistor logic. It's the way that you build the circuit out of individual transistors to create a logic gate. So why do they even call it that? Because aren't they always built out of transistors? And actually, the answer is prior to that era, no. Before TTL logic, there was what was called resistor transistor logic, or RTL. There is diode transistor logic, DTL. And these were kind of early commercialized logic gate structures that were completely replaced by circuits that were essentially all based on transistors. So if you made a logic gate, like let's say an inverter, in other words, you put a logic 1 in, you get a logic 0 out, and vice versa. That logic gate inside is actually a couple of transistors that give you that inversion behavior. So anyway, what the TTL really just means is that logical function was built out of nothing but transistors. And that's the way everything is today.
And you commented about a logic 1 or a logic 0, but yeah, we were talking about voltage. I mean, how do you translate between those?
So hang on to that thought for 1 second. Let me add one more thought to the previous point, just to complete the thought. What became very popular after TTL logic was CMOS. And the difference basically is that in a TTL logic, those were using transistors which were bipolar, basically, if you kind of dig into the architecture of the transistor, versus CMOS. CMOS being a different method of fabricating the transistor. And the advantage to CMOS was that, or is, that it takes much less current to make the gate work. So it was lower power. That's good. The downside is was not the fastest thing in the world. And one of the things that is really remarkable about the microelectronics industry is that every time there is a physical limit that everybody says you can't get past, there's so much money at stake that smart people figure out how to get past it. So, like, if you go back 30 years ago, when you thought about a CMOS circuit, you think, oh, well, that's low power, but it's kind of slow. Well, today, all of the microchips that you find in any of your consumer electronics are all CMOS, and they're all operating at a gigahertz or more. So they figured out ways to make these things remarkably fast. And one of the greatest challenges is also, how do you manage keeping the power consumption low?
So what does CMOS stand for?
Complementary metal oxide semiconductor. So,
and I remember when I was younger, I had a logic probe that I got from Radio Shack. Somebody bought it for me. I wasn't smart enough to know what it did. And I remember it said it could handle CMOS or TTL levels. And of course, now you will often hear people talk about that this is 5-volt logic or 3.3-volt logic.
That's right. And in the early days, the CMOS logic was a higher voltage range. So TTL circuits, the power supply was 5 volts, and the high logic state 1 is 5 volts. In a CMOS circuit, actually, you can have a wider range of supply voltages, like 12 volts or 10 volts. Today, nobody uses that. In microcircuits today, when you talk about CMOS, let's say like the microprocessor in your computer, the pin voltage supplying power to that chip, the external voltage, is much lower. It's probably 2.5 volts, or maybe it's 3 volts or something like that. Once you get on the die in the chip itself, it could be even lower. It could be 1.8 volts or in some cases lower. And the reason is because, remember, power equals voltage times current. So if I can reduce the power, that means I dissipate less heat. I can use a smaller power supply, or if I'm on a battery, like with my cell phone, then I get longer battery life. So if you can reduce the power through reducing the current consumption and or reducing the voltage, you reduce the total power consumption. So that's why, one big advantage of CMOS is it's generally consumes less current, but as you drive that voltage supply rail down lower and lower, you consume less total power. And it's technically very difficult to do that. That's not a trivial task. And so big companies like Intel and others that are like, geniuses at silicon, they're expert at coming up with new technologies that let them do that sort of thing. It's really a hard problem to solve.
Yeah, and so starting out, I mean, the first thing in understanding when interfacing with something is what is that logic level, and then there are also boards that will say they're 3.3 volt logic, but that they are 5 volt tolerant.
Right. So that just means that the input circuit, while the internals are designed to run at 3.3 volts, and that's what they would recommend, that they built the interface to allow you to go as high as 5 volts. Often chips will let you drive 5 volts into them, but won't source 5 volts coming out. They'll source 3.5 volts or 3.3 volts coming out. But I wouldn't assume that the chip could handle 5 volts unless it explicitly says that in the data sheet. So for us in the hobby world, what all this really means is that when you go to build a circuit with logic or a micro controller or a peripheral chip like a sensor, you want to make sure that you match the right components. So let me give you a very simple example. Many of the new chips today that do sophisticated things, like, let's say you're going to make we made this thing one time, I think I mentioned it once in the show, where we had a magnetometer. A magnetometer is a compass, and it's a chip, and the chip sits in a box, and you strap the box to the boom of your antenna. And as you rotate your antenna, this chip knows which compass heading you're pointed at. Well, the electrical interface, the pins of that chip are 3.3 volts, because that's what most of the modern chips are. However, if you hook that up to a traditional Arduino processor board, that's 5-volt logic. So you have a 3.3-volt part talking to a 5-volt part, and that's going to cause a problem. So to solve that problem, you either look for a chip, a magnetometer that runs on 5 volts. Good luck with that, because they probably aren't any. Or maybe you need a different version of your Arduino that is a 3-volt version. By the way, in our antenna analyzer, we use a 5-volt Arduino Pro Micro. You can get a 3.3-volt version of the Arduino Pro Micro, and you could just hook that magnetometer chip straight up to the Arduino, and then it's just all software at that point. But you just have to be cognizant of that. And you'd mentioned, Jeremy, on the previous show, well, what about level shifters? So a level shifter, again, is simply a simple transistor circuit that allows you to interface a 3 to 5 volt circuit. So a 5-volt Arduino to a 3-volt sensor could be accomplished with a little chip in between that allows you to map the two voltages.
And so from there, you kind of referenced this earlier, but there are, I think, fundamentally two different types of interface pins. Actually, well, yeah, that's something else too. Pins can either be inputs or outputs, and in some microcontrollers, you actually have the ability to set the mode of the pin. You can set a pin that is capable of doing either. But then in addition to that, we talk about there are digital pins and then analog pins. And of course, at the end of the day, the voltage is always quote unquote analog voltage. But going back to my threshold question, ...
Yeah. So when we talk about voltages and logics, let's just make that map very clear. So what happened was as circuits got more and more complicated, originally all circuits, like you say, really were thought about in the analog domain. There's the behavior of the circuit over time, and it's maybe a varying voltage over time. Well, when the world started to do a lot more digital logic, the idea was, well, let's abstract away from the voltage and think about it as a logic state. So what I'm going to be looking at is thinking about my logic as a 1 or a 0. And the physical representation of a logic 1 in a traditional TTL circuit, or like the Arduino that we're using, a logic 1 is when the pin measures 5 volts. And a logic 0 is when the pin measures 0 volts or ground. So when we say, oh, that pin has a 1 on it, well, it's not really like a 1. It's really 5 volts. Or in the case of like my magnetometer example, the pin would be 3.3 volts. That would also be a logic 1 in that world. And 0 volts is logic 0. So the reality is, of course, that nothing is 100% perfectly precise. So when they specify a logic 1 in the spec of a chip, they'll say, okay, a 1 is in the range of maybe 5.25 volts down to 4.5 volts, let's say. And a logic 0 is from 0 volts to 0.8 volts. And so anything in between is it's in transition from one to the next. So there's a little bit of a band of acceptability at a logic 1 and a logic 0. So, world's not perfect. But when you think about the logical behavior of the circuit as 1s and 0s, we're really meaning the 5 or 3.3 versus 0 volts.
Okay.
Now, by the way, there's some other possible logic states that we can talk about as well. We'll kind of get to that a bit later. But that's the basic idea. So once you get into the software world, you're only really thinking in 1s and 0s unless you're reading an analog voltage. And we'll talk about analog to digital converters. But so back to your point about input and output chips, one thing that you'll find out about these microcontrollers, if you know nothing about them and you've never used them before, you would assume that out of all those pins, some of them would be digital inputs and some of them would be digital outputs and some of them would be analog inputs and some of them would be something else, like you mentioned a moment ago. That would make sense. But the way they actually build these microcontrollers is a little bit fancier and a little bit more powerful than that. What they'll do is they'll typically put a interface circuit behind the physical pin on the chip. And that little circuit is a switch. And that switch allows them to connect different kinds of interfaces to that physical pin. So that's what enables you to assign that pin to be either an input or an output. In many cases, that chip might serve another function. So like on most of these microcontrollers, the analog voltage inputs can be on several pins. So a pin could be a digital in, a digital out, or an analog in. And in software, you have to declare what that pin's behavior is going to be. And when you do that, what happens is it writes some ones and zeros into an internal memory address that you never see as a user typically. You write some ones and zeros to a register, is what it's called, and that will then force that pin to behave like an input or behave like an output or behave like a voltage input or whatever it is that you're telling it to be. So that is one little extra bit of complexity. So when you look at the data sheet, you'll look at a pin and go, wait a minute, this pin says input, output, analog to digital converter, and maybe something else too. Well, how do I get all four things? Well, you can only get one at a time. So you have to decide what that pin is. So, and the reason they do that is the physical package only has so many pins. And if I'm building a project, I might want to read 10 voltages. Maybe on your project, you want to read no voltages. You just want a bunch of digital inputs and outputs. But you can use the same chip for both of those projects and just program them differently in software.
Okay, so give us, before we move into analog pins, talk about, give me some background on digital inputs.
Yeah, so the simplest possible pin configuration is a digital in or a digital out. And simply what that means is the digital input means I'm going to allow a signal, a voltage, to come into this pin. And in software, I'm going to look at that pin and I'm going to either say it's a logic 1 or a logic 0. If I measure that it's like around 5 volts or 3.3 volts, again, depending on the part, I'm going to say that's a logic 1. If I see that the voltage on that pin is closer to ground, then I'm going to say it's a logic 0. And in fact, in the software, if you say, give me the value of that physical pin, it'll come back as a character 1 or a character 0 or a number of 1 or a number of 0, depending on the compiler. And that's the logic value you're reading. So when you say a digital input, you'll never get a voltage. You'll only see that converted to a logical value.
Yeah, or high or low.
Or high or low. I mean, they might call it different things in the compiler, but it's essentially, it's a 1 or 0 expressed as high or low or 1 or 0. Now, a digital output is exactly the same idea, but going the other way, where you're going to tell the pin to either put 5 volts on the pin or push that pin to ground so that some external thing could look at that pin and see that value. So let me give you some examples. So let's say, why would you use a digital input? Well, let's say I've got a on my Arduino for the antenna analyzer, I've got some push buttons. Each one of those push buttons is hooked up to a different pin. And that push button, of course, there's two sides of the button. One side of the button goes to the pin of the microcontroller, and the other side of the button is wired to ground. Now, if I set that pin on the microcontroller as an input and I press the button, I'm going to close the circuit and you'll see ground applied to that pin. And if I read that pin in the software, I get a logic 0. If I let off that button, what happens?
Well, it would go back to high. Well, actually, it would be disconnected.
It would be disconnected.
And so I'm assuming there's going to be some like floating voltage.
Yeah. So what happens is if you read a pin on a microcontroller that has nothing hooked up to it, it's not deterministic. You don't know what it's going to read. It might be a 1. It might be a 0. It might go back and forth over time. You don't know. What determines if it's a 1 or a 0 is kind of what's around physically, what's near that pin that might influence it. I had a circuit one time where, and I'm sort of embarrassed to admit this, but I had a logic gate on the circuit board. This is like 10 years ago. And I read the value of the pin, and it read it correctly, and everything worked great. And one day it stopped working, and I couldn't figure out why it stopped working. And I accidentally touched the top of the chip with my finger. Now, the top of the chip is a piece of plastic. It's not conductive. But the fact that I put my finger on the top of the chip, there is enough stray capacitance in my finger that it caused the input pin that was not properly connected to float to a logic 1 or 0, whatever the other state was. And it kind of blew my mind that I forgot to hook up this one pin. And it was goofing up the behavior of the circuit. Now, you could say, well, okay, that's a simple problem to solve because I just need a switch so that in the up position, maybe I have a single pole 2-position switch. In the up position, one circuit is complete, and in the down position, the other circuit is complete. And I have one side go to ground and one side go to 5 volts, and the switch just puts 5 volts or ground on that pin. That would work perfectly fine. The more common way to deal with it, and the better way to deal with it, is actually to use what's called a pull-up resistor. So if I have my input through a switch, and the switch goes to ground, I don't need a fancy switch, just a single pole, single throw switch. And when I press the switch, it closes the circuit, and I present ground to the pin. When I let up on the button, it's now going to float. If I take a high-value resistor and hook it up to that microcontroller pin, and then hook the other end of the resistor to the power supply rail, the 5 volts, when I let off the button, what happens is through that high-value resistor, I will present 5 volts to the input of the microcontroller. So it'll see a logic 1 when my button is up. When I press the button down and complete the connection to ground, now it'll see ground. Now you could say, well, isn't that going to create a dead short? Well, it creates a short between 5 volts and ground through let's say a 10,000 ohm resistor, which looks like not much of a short. That's a pretty high resistor with very little current flowing through it. And the path to ground will swamp out the resistors pull up to 5 volts. Now, when you do that, that also means there's no intermediate questionable state. It's either in a 1 or a 0, not floating at any point. So that's the more common way to do it. And you'll see that on our antenna analyzer. When you press a push button, it grounds the circuit. And when you let off the push button, that input is pulled up to 5 volts because of a pull-up resistor.
So I've heard pull up, and I've also heard pull down, which I'm assuming does the opposite.
Yes.
Is there a reason why I would use one over the other, or is it just based on, I mean, it's in my limited understanding, I would wire something up one way with either a pull up or pull down, and then just do the opposite in software based on.
Yeah, right. So you could do it a couple different ways. One is you could do a pull downs, like everything I just described, but let's say the switch is wired to 5 volts, and you have a resistor from the microcontroller pin to ground, a 10K resistor. When I press the button, I apply 5 volts. It's a logic 1. When I let up off the button, the pull down resistor pulls that input down to ground. So those are exactly equivalent kind of circuits for all practical purposes. The convention, 99.9% of the time, is that you pull the inputs up and you use ground as your switching input. Now, to your point about software, in software, the first thing you're going to do is read that raw value off the pin. And let's say you read the value and you get a logic 1, which means it's at 5 volts. You can then say something like, well, if pin is 1, then do something. If you want to invert that, you can do that in software. You could just say, well, X is the value of the pin. It's a 1. X is now 1. And then you can just say, depending on the compiler, X equals not X. In other words, the value of X is going to be replaced by the inverted version, the not version of that, so a 0. So if you want to then use that logic 1, map it to a 0, and then use that in your program because that's more understandable, you could do that. I know that sounds a little jumbly, but yes, you can always change the polarity in software easily if you want to.
So I'll just comment that for these concepts where I'm able to find good, easy to understand links, they will be in the show notes. So for instance, SparkFun and Adafruit are always great resources for these types of topics. And I'm including links to a lot of the learning materials on sparkfun.com as we discuss these things.
So just to wrap that, I mean, this is kind of an overly complicated explanation of a really simple concept. And 99% of the time, what you're going to do for a push button is you have a resistor pulling it up and then a switch to ground, and you're kind of done. So it's really very simple.
Okay. Anything else about inputs?
Well, for a simple digital input, let's just start with that, and then we'll look at some more complicated things later.
That sounds good. Yeah, because we haven't really talked. We've talked about how an input works, how it tells that it is high or low, but we haven't really talked about applications. So now if we switch over to digital output pins, what do we need to know about those?
It's the same idea except flipped around, but you don't need to pull up or pull down because you're going to be driving the output, either pulling it to zero, to ground, or you're going to be driving it to the voltage supply line, 5 volts. So in that case, in the program, you just have a line of code that says, set this output pin to be a logic 1, and then puts 5 volts on it, or set it to be 0, puts 0 volts on it. And a very simple example is to light an LED, which is the hello world of the microcontroller world is light an LED, blink a light. So if you take an LED and you put it across the 5-volt power supply, you burn it out. So you got to put a series resistor in line with the LED so that you limit the current, drop the voltage. So let's say you have a 5-volt supply. You might put about a 330 ohm resistor in series with the LED, and that voltage will light the LED. Well, same thing is true for the microcontroller. If you take the positive side of the LED and connect that to the microcontroller output pin, and then you put the negative side of the LED through a resistor to ground, and you put a logic 1 on the output pin from the software, it applies 5 volts and turns on the LED. It's very simple. So if you want to make a simple test program to write a little loop that says turn on the light, wait half a second, turn off the light, wait half a second, and then loop forever, then your light blinks. And it's simply just putting 5 volts on that pin and taking it off and putting it on and taking it off.
And if you have an Arduino board, most of them have an onboard LED that I think is tied to pin 13. And this is, we've talked about before, the Blink program, which, as George said, is Hello World. But this is usually every Arduino tutorial in the universe starts with getting you to blink the onboard LED.
Yeah, and it's great because it's a trivial program, but it proves out that you can actually compile your program and download it into the part and get it to do something. Now, the one thing to be careful about with an output pin is that there's a maximum drive current. In other words, there's a maximum amount of current that could be supplied out that pin. And for most microcontrollers, it's on the order of 25 milliamps, which is adequate to light an LED, but not a lot more. So if I had, let's say, a 5-volt relay, and I wanted to turn that relay on with my microcontroller, the current necessary to actuate the relay is more than what that part can deliver. So that's not going to cut it. You're going to need to buffer that output somehow to switch that relay. And by the way, buffering outputs for that sort of thing is really simple. You can use a simple transistor and a resistor to buffer it, or there's chips that are designed specifically for this purpose. So when you look at the low voltage disconnect design, which we haven't published yet, but what you'll see on there is the Arduino has an output pin that goes to the latching relay. So we're using a relay that switches between on and off by pulsing 2 different pins. And that means I need 2 outputs, one to put the relay in position A and another pin pulse to put it in position B. 2 outputs, but if I just hook the Arduino to the relay coils, it wouldn't have enough juice to flip the relay. So I have to have a buffer transistor in series with that. Now, and by the way, if you use a buffer transistor, a single transistor, it's actually going to invert the output's logic. So if I take let's say an NPN transistor, a common bipolar transistor like a 2N2222, and if I put 5 volts out of my microcontroller into that transistor on the base, the collector of the transistor will have the opposite logic value or voltage. So 5 volts on the base of that transistor will pull the collector to ground, assuming the emitter is hooked to ground. So a logic 1 out will pull that pin to ground, and if I put a logic 0 on it, it will release that transistor and it'll float to, whatever, no voltage, essentially. So that means that on the relay, I can apply ground to the relay. I cannot apply 12 volts to the relay unless I use a different kind of transistor. So anyway, that's why a lot of circuit actuation in relays, you will put the coil voltage on the relay on one end of the relay, and then you'll be switching the low side. You'll switch the ground side because you're going to go through a buffer transistor, and because a logic 1 on the output of a microcontroller causes that transistor to conduct, pulling that pin to ground. So that's why you're switching the ground side.
Gotcha.
Anyway, so the simple interface between a microcontroller and a relay is a resistor and a transistor, and it's very trivial.
Okay. So those are the fundamentals then between that. So, I mean, basically the digital pin for an output, I can switch it high and low. One of the things that if you do the Blink tutorials, because the first thing is getting it to turn on and off, and then they start teaching you about duty cycle as far as how long am I leaving it on, how long am I leaving it off? Like what are the time constants that you're using for those things? Let's move on to analog pins.
Yes. I love analog pins.
Well, first of all, here's something that, again, I think I referenced this in a previous episode. The Raspberry Pi has none.
Right. The Raspberry Pi only has digital I/O. Whereas the Arduino and it, because of its core processor, an Atmel or an ARM processor, they have analog to digital converters built into them, and PICs also do. And a BeagleBone, which is kind of like a Raspberry Pi, it's got analog to digital converters built in. So if you're going to read a voltage, you need a thing called an ADC, or an analog to digital converter. And they could either be built into the processor chip you're using, or they could be external and then interface through other digital connections to the processor.
Well, cool.
Yeah, and we talked a bit about ADCs in the last show. I don't know how much we want to go through it here, but the simple story for those of you who didn't listen to the last episode, what an ADC does essentially is it measures the voltage between 0 volts and whatever its maximum rating is, and typically its maximum rating is the power supply voltage that supplies power to the chip. So if you have a 5-volt Arduino, you can measure between 0 and 5 volts. So what the ADC does is it looks at that range from 0 to 5 volts, and depending on where the voltage is in that range, it will give you a number when you read the value of that pin. And let's say if you use a 10-bit ADC, which is typical in microcontrollers, a 10-bit ADC, so 2 to the 10 power is 1024. So that means that I will take that 5-volt range and break it down into 1024 slices. And at whatever voltage I read, I'll give you that number. So I can do the math easily. Let's say you read 2.5 volts, which is exactly in the middle of the range of the ADC. What number do you think the software is going to give me?
513.
Yeah, it'll be like 512, 513, somewhere around there.
Or 511.
Yeah, because it's 0 to 1023.
It's 0 to 1023. So
yeah. And of course, if it's 20% into the range, 1 volt out of 5 volts, it'll give you 200 or whatever, 1024, 200. So now when I read that ADC value in software, let's say I read the 2.5 volts and I get a number of 512, let's just say. And if you have your software report that number on an LCD display, or for example, you go, I now have 512 ADC units. What does that mean? So what you would further do in the software is you would then convert that ADC number into a meaningful value on your display. So if you said, well, I'm making a 5-volt voltmeter, then you would write a little piece of code that then converts that 512 number into 2.5 to display that on the screen. Now, the other thing to note about ADCs is you might say, well, that's great, but what if I want to measure in the ham radio world, I want to measure my battery. So in our low voltage disconnect, I want to measure the battery's voltage, and typically that's going to be somewhere between 8, hopefully not, but 8 to 14 volts. Well, if I measure 14 volts and shove that into my processor, I'm going to have a fuse. So it's going to blow up the part. So I need a way to scale that down. And a very, very simple way to scale it is by putting a voltage divider in front of the ADC. And a voltage divider is just 2 resistors. You pick 2 resistors with a resistor value ratio such that the maximum voltage range you want to measure can be converted down to 5 volts. So if you said, well, what do you think the highest voltage is you'd measure in the voltage disconnect circuit?
Well, I mean, our radios are rated at 13.8 volts plus or minus 15%. So I can't remember what the top value is, but it's over 15 volts.
Okay, well, let's give it some headroom. Let's say 20.
Okay.
So let's say
I like that. That's a good round number.
Yeah, we're going to measure 0 to 20 volts, and that means I need to have a 4-to-1 voltage divider. So I need 2 resistors that give me that ratio. So, that's how you make a voltage divider. And by the way, one note is this is the one time when you want to use high precision resistors. So when you buy a resistor, usually they're like 5%. In this case, you want to use a 1% resistor because the variation in these values will throw your reading off by that variation. So resistors like this are cheap, so why not get 1% resistors and you make a voltage divider. You've now converted your 0 to 1023 number in the ADC you read in the software. Now instead of that meaning 0 to 5 volts, it means 0 to 20 volts. Now the one downside of that, by the way, is each slice, each single digit of that ADC's value is now 4 times more coarse. So before I measured 0 to 5 volts in about 1,000 steps. Now I'm measuring 0 to 20 volts in 1,000 steps. So each step is 4 times bigger, slightly less resolution. If you're measuring the voltage of your battery in your station, it's perfectly adequate. If you're going to do a very fine, high precision test equipment, that's not good enough. And you'd want a higher precision ADC with more resolution. But for most of our applications, the ADCs that are built into the Arduinos or the PICs are fine.
In thinking about this, when we look at microcontrollers, do they have analog outputs?
Well, there's 2 kinds of analog output typically. There's either a DAC, a digital to analog converter, or there's a pulse width modulator, which is kind of a way to approximate analog output. Microcontrollers generally you almost never see a DAC in a microcontroller. It's a separate chip that you would buy and hook up to your microcontroller. And what a DAC does is you shove a value into a control register on the DAC, and then it will create a voltage on the output. So I cannot even remember seeing a microcontroller with a DAC built in. I'm sure they exist, but they're the ones that we typically use in the hobby world. No, they don't. But you could have an external one. If you're making a circuit where you want to vary what appears to be varying a voltage, like if you want to dim a light or if you want to control a motor, the way that's frequently done with these kind of microcontrollers is with a special digital output called a PWM, or pulse width modulator. And a PWM is simply a digital output that switches on and off rapidly. And what you're changing on the PWM is the duty cycle. So in other words, when you think about a normal digital signal that goes high and low and high and low and high and low, you would assume that it goes on for a period of time and it goes off for a period of time, the same amount of time. That's called a 50% duty cycle. Half of it's on, half of it's off. If you start to change that duty cycle, so let's say it's on for 90% of the time and off for 10% of the time, then if you were to hook that up to an LED, for instance, the LED will appear to be brighter because you're leaving the voltage turned on more, even though the voltage is not higher. But there's some persistence in the LED in your eyeball too, so that it appears that the light is on all the time. If the frequency of the switching is fast enough, it looks like it's always on. But in fact, it's off a little bit of the time. But it's so fast you just can't tell.
Yeah, and I mean, that's a byproduct of the fact that, as current goes through an LED, it does take time to get to a brightness. And so I seem to recall a toy that we would have all had growing up where you have to keep kind of, or it's like passing a balloon along, right? Like you're tapping it slowly. Then that's a pulse, and based on that's a terrible metaphor. I mean, but the point is you send current into it, and for the time that the current is going through, the LED is moving from brightness A to brightness B, and then you turn the current off, and when the brightness starts to dim out of it, it goes down a certain point, and you've charged it again, and it just kind of keeps pumping like that, and it's because of the. I don't know what. I think in transistors, it's this. Is it the slew rate, which is how quickly the thing responds?
Well, there's a rise time and a fall time.
Okay, that's probably a much better term. Again, squib.
Well, and by the way, in an LED, depending on the application, your eyeball has a little bit of persistence to it too. So when if the LED is flashing at 10,000 cycles per second, there's no way you're going to be able to distinguish that. So to you, it looks like it's just on. And, if you had a fast enough camera, you'd see it going on and off. Go ahead.
One thing, just to make sure, I mean, technically, pulse width modulation is a mode going to be used on a digital output, right?
Yes.
Yep.
Now, you could also take that pulse and you could put it into like an RC circuit, resistors and capacitors, and you could charge that capacitor and look at the voltage, and that will look like a fairly constant voltage because the capacitor is constantly being slightly recharged. So you can kind of smooth out that wave a little bit by using a capacitor. But depending on what you're actually doing. So if you have you're doing a fancy light show with let's say you've got these 3-color LEDs and you want to make different colors and you want to make different brightnesses, you can control all that stuff digitally. There's actually no analog voltage applied out of the microcontroller. It's all done in the digital world. So in a way, there's kind of you can get to an analog output in a way by using those sort of things. When we do the repeater controller, by the way, so there's a pulse width modulator in the PICs that we use in the repeater controller, and we generate audio tones that actually sound pretty darn good by generating them digitally and using the PWM to do some tone generation. So it's not trivial to do it, but it's not that big a deal. And, so there's ways to do some analogish kind of stuff with those.
Yeah, and that's one of those things, though, that kind of I've never really been able to wrap my head around it because I had always assumed, again, you're going from ground to 5 volts, ground to 5 volts, ground to 5 volts, and you are controlling how rapidly are you transitioning between the high state and the low state and how long you're staying in each state, right?
Exactly.
And I've never really understood how that approximates quote unquote analog voltage differential. Cause I would assume that's that's going to be determined more by the thing you're interacting with than it is, just the fact that okay.
Yeah. That's true. So the way the thing you're interacting with responds to that. So let's say, for instance, if you're poking at a device which has a long persistence, in other words, if I give it a voltage and then take it away, that voltage will still have some residual effect on that thing, then I could make it appear to be like an analog control voltage when in fact it's just pulsing it. If the thing on the other side is super fast and could discriminate between every single pulse at 10 kilohertz or whatever frequency, then it's going to look like a bunch of 10 kilohertz pulses. So if you put a 100 megahertz scope on a 10 kilohertz signal, it'll look like a square wave. I mean, it'll definitely be able to discriminate each individual wave transition.
Yeah, and actually, the very first time that I got an oscilloscope and I had an Arduino, and this is when I was very first starting to play with this several years ago. I had the blink example set up on an external LED, and at that time I was running. I think it was like it was an LED that could be red, green, or if you turn them both on, it was yellow. And I set PWM to adjust the brightness, and you watch the scope, and you just saw the rising, the width of the high pulse just get wider and narrower, wider and narrower, wider and narrow. Like the wave wasn't actually changing per se. But that was interesting.
Yeah, and so when you look at it on the scope, you go, "Oh my God, this is made up of a string of pulses." If you hooked up an incandescent bulb to that, assuming it handled the current, an incandescent bulb, when you flip a switch, the light bulb kind of gets bright and stays bright, and when you flip it off, it takes a second or so for that filament to de-energize and the light to go away. Well, if you pulse that incandescent light bulb at a 10 kilohertz, it's going to look like it's got a voltage on it, because it's got a persistence to it. When the voltage goes away for a very super small period of time, it's still going to be glowing because it takes a longer time to decay than the frequency of the pulses. So
to kind of recap, going back to, we covered digital inputs really well as far as understanding that I'm using pull-up resistors. I have switches, and I'm going to basically be able to use a microcontroller or a single board computer to have some type of an event fire off in that case. For the outputs, there are the ability to just set things high and low, or you could do this pulse width modulation. We've kind of covered what you would interact with there. Pulse width modulation is also used to control, say, direction and speed of servos or stepper motors. But oftentimes, like you said, these are the chips themselves are very low current applications. So you're often interfacing with some type of a device, and I believe those are often called drivers, right?
Mm-hmm. That's right.
Like in the LED example you talked about, having a single driver or a buffer with a transistor, but there are a lot of boards you can get that will take those digital signals, and that's literally when we talk about signaling. It is literally just a signal to another device, which is built to handle more power to say, okay, you want me to turn on, you want me to open a relay, and of course, I can't route 110 volts through my microcontroller. So the relay has a 5-volt signal or responds to a 5-volt signal that when it gets the signal, it says, okay, go ahead and open or close, depending on if it's latching or not, right? Mm-hmm. And then you will often see, and again, I'm mostly familiar with Raspberry Pi and Arduino, but there are shields that are available that may be relay shields, like we talked about when we were discussing building the idiot switch. There are also servo drivers and motor drivers where they take 5 or 3 volt signaling, but then you apply 12 volt to that board, and then that ultimately controls the power going to those devices.
Yeah, exactly. And the example of the relay is I think the perfect baby example. If you have a relay, let's say it's even the same voltage as your microcontroller, a 5-volt relay, that coil may energize when you're supplying 5 volts at maybe 100 milliamps. And if your microcontroller can only supply a maximum of 25 milliamps, which is typical, you won't have enough juice to throw the relay. If you put a transistor in series with that power lead to the relay, but the transistor is not the little itty-bitty transistor size that's in your microcontroller. It's a bigger, beefier transistor. The transistor is essentially acting as a switch. It takes very little current out of the microcontroller to bias the gate of that transistor, turning on the transistor, which makes it look like a big switch, to ground. And that transistor can handle an amp. Well, now you're pulling 100 milliamps through a transistor that can handle 10 times that much current, no sweat. And the amount of current coming out of the microcontroller might be just a few milliamps in order to bias that transistor on. So that transistor is now your buffer transistor. So it handles all the current for you.
Going back to analog inputs, I mean, it seems like the most common application of that is literally you're reading a value and you're going to do something with the data of that value. Like you're measuring something in the system.
Right.
Like, are there really any other common applications for reading, and doing analog to digital conversion? I mean, are there any other things that I'm going to do with that, or is it literally I'm just trying to get a data value to react to?
Well, that's essentially what you're doing. You're in the data that you're reading is the voltage. So whatever the circuit is doing in the real world, there is some voltage that you want to read, and the ADC is telling you what that voltage is.
Well, actually,
converting it into a number so you can process it in software.
And I actually just thought of probably what is one of the simplest demos of this is if you were to get one of those, what are they, cadmium sulfide photoresistors? Mm-hmm. If you were to just get one of those and stick it between, 5 volts and an analog input pin and just move your hand around it and you were using the serial output to see that value as it changes, then, I mean, that's a pretty good demo.
Yeah, you'd see it dance around. We made a trainer board some years ago for learning how to program PIC microcontrollers, and the example we used for an ADC was a little potentiometer, and the potentiometer, a pot, you would hook up the high and low, the two ends of the pot to 5 volts and ground, and the wiper of the pot would go to the ADC input. And when you had the pot in one end, it's ground, and as you swept it across, it would go all the way to the 5 volt side. So continuously from one end to the other, you'd go from 0 to 5 volts. And you look at, we had an LCD display, and the test program read the ADC value and just displayed it on the LCD. And so when the pot was all the way to the left, it would say 0. And as you move the pot all the way to the right, the number would increase up to 1023. And guess what? When the pot was in the middle at 2.5 volts, it gave you 512 or whatever around there. So that's the most elementary example. Now, what might you use that for? So in the low voltage disconnect, we use ADCs to measure the battery voltage to decide whether or not we should have a low voltage disconnect or not. In the antenna analyzer, we measure the voltage on the little bridge circuit to figure out if there's more energy going to the antenna or bouncing back from the antenna, and that's how we determine the SWR. So they're used for, like an infinite number of applications where you're trying to measure a voltage. If in the real world you're trying to measure something that's not voltage, like current, then you're going to come up with a circuit that converts current to voltage, and you're going to measure the voltage and do the math to convert that.
I can't put 20 amps through an Arduino?
Once.
That's when the smoke comes out.
Yeah, exactly. So you don't want to do that. And so if you have an ammeter, what you're really doing is creating a circuit that's going to measure the voltage drop across a shunt, for instance, and you're going to use Ohm's law to calculate what the current is based on the voltage drop and the known value of the resistor. So again, you're measuring voltages, but in your software, you're going to convert that voltage measurement into current and display the current.
Well, cool. So I think that's a pretty good overview of the basic, the basic states and modes and usage of these pins. And again, there will be links in the show notes to a lot of great tutorials at SparkFun on these concepts. But George, I think when we come back from the break, this is all well and fine, but we haven't really talked about how do I interface with a temperature sensor? How do I interface with, through only 2 wires with a simple LCD? I mean, there's a lot of applications that kind of get a little bit more complex, that are a little bit more specialized usage of the pins on these devices. And I think when we get back from the break, we should deep dive on that.
Yeah, that sounds great. Let's do that. Be back right after this.
The Workbench is sponsored by our friends at CADsoft. They're the makers of the Eagle PCB design software, the very software George used to design the Pactena Classic, Pactena Mini, what him and Barrick are using to create this new antenna analyzer project for you here on the Workbench. They got hundreds of parts libraries, tons of reference designs, and a monster huge user community. Eagle's a great choice for your next ham radio project, and you can get your free copy of their software today. Click on over to cadsoft.io and start getting your project put together today.
All right, we've covered the basics of digital inputs and outputs and analog inputs, kind of have a good understanding. Admittedly, there's a little bit more reading to do, and we've provided links for that stuff in the show notes. But, I mean, at the end of the day, blinking an LED is cool. Making a motor spin is cool. Closing a relay is cool. But I really want to go out and build a device that does a thing.
Okay.
I want to interface with something that's a little bit sexier than, a photodiode.
Yeah, right. Well, and the thing that's so cool about electronics today is there are hundreds or thousands of chips out there that somebody's designed.
Billions
and you can buy for a few bucks.
Billions.
Yes, that's right. And so you could buy all these like fancy, like I mentioned, the magnetometer, the compass. Well, that's a chip with 4 pins on it. You've got ground and 3-volt supply and 2 data pins to communicate the value of the compass heading. So most of these sophisticated peripheral chips don't use analog and single like on-off digital inputs. They use specialized communications interfaces, serial communications interfaces. So yeah, let's get into that.
So let's start off with, and this is just one of those things from computers. We remember in the old days, our computers had serial ports. We know our radios have serial ports, and we know that we used to connect printers to parallel ports. At the very basic definition, what do you mean when we talk about a serial?
Well, serial simply means that I'm going to send information over a wire one piece at a time, and I'm going to be sending multiple pieces. So if you think about the old RS-232 serial interface, what the serial part meant was I'm going to send one bit at a time. So if you have a character like A is represented in ASCII by 8 bits.
That was your original call sign.
A, correct.
A, yeah.
Before W and K and a number. Before Hiram Percy Maxim. So if you're going to send the character A, you're going to send a series of ones and zeros, and you send a 1, the first bit, then the second bit, then the third bit. So you send the bits serially as opposed to in parallel. So the other way to send 8 bits of information is you have 8 wires, and at one point in time, like now, those 8 wires each have a 1 or a 0 logic on them, and there's an 8-bit value. Well, if I'm going to send a character over a wire in parallel, I need 8 wires. Well, I probably need more than that because I need ground and so forth. If I want to send that on fewer pieces of copper, then instead of sending 8 bits at one instance, I'm going to take those 8 bits and send them one at a time. I'll send bit 1, then bit 2, then bit 3, then bit 4, then 5 and 6 and 7 and 8. And it turns out in RS-232, not only do you send the 8 bits, well, it's really 7 bits for the character and a parity bit. You have a start bit and a stop bit. So you're really sending about 11 bits for every character. And those are sent sequentially or serially over that cable. Now, why would you want to do it serially? Because you use a lot less wire. I mean, literally, it's less copper. Now, inside a electron...
If there's one thing I've learned, it's that electrical engineers tend to be stingy. less power, less copper, smaller space, fewer components.
Well, if not, your iPhone would be as big as a refrigerator's. So it's the pesky customer that demands this. If it weren't for that, you'd need a refrigerator cart to haul it around. So think about like an old computer. If you're old enough to have been around, decades ago when microprocessors were first popular. If you think back around like the 8080 or the Z80, those 8-bit processors, and if you looked at a CPU board, you would have one chip that was the CPU. You'd have a bunch of chips that were the RAM memory chips. You'd have a bunch of chips that were the EPROMs, where maybe the bootloader or whatever was stored. You'd have another chip that was the serial interface for the terminal, the UART. You'd in other words, every function just about of the computer had a separate chip or chips, and the way all those chips talked to each other was on a parallel bus. So you'd have to have, let's say, 8 to 16 address lines, because you had 8 to 16 bits of address. You had at least 8 bits of data. You had some read-write control lines and some clock signals, so that you would have to haul something on the order of 30, 40, 50 wires between each of the chips to make it all work. And that means that the boards were big, and all of that wiring also, to some extent, helps determine the maximum speed you can actually make all this stuff work at. So as electronics got smaller and smaller and the sophistication of the components was going up, there was a need to simplify the interfaces between these chips. One of the most popular ways to do that was invented by Philips. They invented an interface between chips called the Inter-Integrated Circuit Bus, IIC, commonly referred to as I2C or I2C. And the idea was, okay, rather than haul 60 bits, 60 wires between 2 chips or 10 chips, can we use this serial technique to serialize the data and go from 60 wires down to 2 wires? And they invented this I2C bus that has 2 wires. One wire is a clock, and one wire is the data. And if you're going to send data from one chip to another, it takes the data, converts it to a serial stream, shoves it over the wire, it decodes it on the other end, and then the function takes place. So
well, hold on, I have a question.
Yeah.
So you said there's a data line, there's a clock line. Obviously, ground has to be involved somewhere.
Yeah. So there would be ground. There'd be.
It seems like everybody's always like ground never counts.
Well, it's just assumed that everything is grounded. It just like it's assumed that everything is hooked to a power supply. So if you're all on the same circuit board, then you would just think, well, all I have to hook to the microcontroller is these 2 pins for data and clock, because the power and ground's already hooked up. If you were going to go off the circuit board to a second circuit board, then you would have to haul power and ground to that other board as well. So you need 4 wires.
That's the reason that I 4 wires? Oh, power and ground. Duh.
Right.
Sorry. And the reason I bring that up specifically is, we've talked in the past about breakout boards. Mm-hmm. And I2C is a very common method of interfacing with breakout boards. And it's just one of the several serial interfaces we're going to talk about here. So you have a clock line, a data carrying line, power and ground are handled however. One of the things that I remember about I2C is that devices on that bus, I'm going to use words I've heard. There's an I2C bus, and individual devices on that bus have an address. Mm-hmm. Like a unique address.
That's right.
Talk about some of those features.
Yeah. So the way this works is, like you said, each part has an address. The data that goes across these serial wires. Let me give you an example. Let's say, for instance, I might have a memory chip, and that memory chip is going to be used to store some information. Let's take our low voltage disconnect. Let's say I want to monitor the voltage coming into that circuit, and I not only want to monitor it and do something real time like open the relay, but I want to log that data. So I need to store that information somewhere. Well, where would I store it? I could store it in the microcontroller, but there's some limited storage there. Maybe I want to store it in an external chip. So I go look in the DigiKey website and I find a chip where I can store data, and I'll pick an I2C chip, and it'll store maybe a megabit of data, and so then I hook up a power ground and the data and clock wire, and so that's it. Those 4 wires, I'm done. Now, how do you actually talk to the chip? So when I send data from my microcontroller to that chip, the I2C protocol requires multiple steps to ship the data over to the other chip. And in I2C, you're typically sending 8-bit bytes of data. And if I'm going to send, let's say, a byte of data to be stored in a memory location, I have to send it like 5, 6, 7, 8 bytes of data to make this work. So the first thing I'm going to do is send a byte out on the I2C bus and say, I'm going to grab the bus and send a information to chip with the address of whatever, 40 hex, whatever that address is. Now, when the manufacturer of the memory chip makes those chips, what they'll say is that all chips of this part number have this address. So that's in the data sheet. And so to write your code to say, I need to send the first command that says, attention chip with the following address, please pay attention. So that's 1 byte. Then, depending on what the chip does, there may be control bytes. Like if it's a memory chip, I could either read data from it or I could write data to it. So maybe the second byte I send over says, I'm going to write information to you. The next byte that you send might be the address of where you want the byte to be stored in that chip. The next byte you send might be the actual data byte that you send to the chip. The next byte you send is the stop byte that says, okay, transaction is done, please execute it. So in order to send 1 byte of data to that external RAM or that external EEPROM chip, I may have to send it 6 or 7 or 8 bytes. So there's overhead of a serial bus. There's overhead because I have to convert any of the signals that might have been individual pins to be data in this series of bits that I'm sending over to it, which means that that's not the fastest way to architect something. If you do something in parallel, it'll be inherently faster. But in a lot of applications, speed is not the problem. The problem might be the physical space on the circuit board, where you want to only use 2 wires because I'm only going to send a byte of data every minute. That's so slow, no sweat doing that serially.
So one thing to point out, because, when you're talking about sending the different bytes, and I've seen in several data sheets, like they will specifically talk about how you have to assemble these messages. And if you're building a microcontroller, and you're interfacing with these chips natively, and you're writing firmware for these things that are not using something abstracted like Arduino, and you're actually writing machine code for them like you would on a PIC, that sounds really hard, especially if you're somebody like me. That sounds difficult. But fortunately, Arduino gives you the libraries where you don't have to do a lot of the overhead of that management, and often you can just tell it, here's the data I want to ship, and here's where I want to ship it to.
Well, that's true for an Arduino. That's equally true for a PIC, by the way. So don't assume that you have to go to the low level.
I'm the Arduino. Well, yeah. But you could go to low level on an Atmel processor. But my point is, I'm the Arduino guy. You're the PIC guy. So I'm sorry, I'm not trying to denigrate PICs. I didn't have experience with.
No, I'm just saying that the if you look at like the PIC code that I wrote to talk to the magnetometer. It's the exact same equivalent library that you have in an Arduino. It's different syntax, but there's a start I2C transaction subroutine call, which is like start, and then there is address, data, stop, whatever. The same thing you'd have in an Arduino script. You'd write the same thing in the with a compiler on the PIC. So yeah, the what you're really referring to is using these. Higher level, like symbolic names, to refer to lower level patterns of bits. So on a let's say one of these memory chips, if I were going to do a memory write, so I'm going to say attention chip, address number 40, I'm going to write data to you. Well, when I say write data in my source code, what the compiler will do is create the right patterns of ones and zeros that gets squirted out to the other chip to tell it it's a write command. So you don't have to look it up in the data sheet. So yeah, it abstracts that like minutia, because frankly, you don't really care. I mean, do you really want to know what the bit pattern is to tell the thing to write? Not really.
No, I mean, not unless I am trying to absolutely optimize for speed or performance or something like that.
Yeah. Yeah, or if the library is wrong, or if you're porting that library to a different chip and the commands are different. It could be that the write command is 0001 and in a different chip the write command is 1000. So okay, I just need to change that so that it has the right format. But yeah, in general, those libraries abstract all that nonsense away. So actually dealing with an I2C chip is really pretty simple at that level. It's just, begin the conversation with device at address X, do this function, here's the data, or retrieve the data and assign it to a variable. And it's that simple. So one reason this all works really well is because A, there's libraries already ready to go. B, those sensors are little itty-bitty dedicated microcontrollers in their own right. So when I talk to the Compass chip and say, give me your heading, it responds with data that's like 260.3 degrees. So it figures out its direction, and its little baby microcontroller inside converts that magnetometer analog reading into a number because it has a built-in ADC. And then it takes that number and stuffs it into a message that is sent back to me over the I2C bus, and I just read that number and stick it into a variable. So you're literally saying, chip number 42, give me your heading, and it squirts back 53.5. and you're done. It's that simple.
Yeah, and that's kind of the cool thing, especially with the breakout boards, right? Those libraries to do that really do make it that simple. One other thing I'll add, just that was interesting to me, is when I had done a project previously where I was using these high resolution lux sensors, basically to detect brightness, and I was using this for building a proof of concept like solar panel array mover, so that it would aim a solar array at an optimal position. The sensors that I bought, if I had one device trying to talk to all these different sensors on the I2C, which I'll ask a question about here in a second, if they all had the same address, what would happen? Because
it would be a mess.
Because
it wouldn't work.
Yeah, in this particular case, on each one of the breakout boards that Adafruit made for these, there were pads. And the pads were like these little solder pads with a really teeny tiny, printed, copper trace between them. And when you got the board, you took an X-Acto knife and you cut one of those pads, and that would actually set the address, because the chip on these were designed to have 3 addresses. So it would be a mess if they were all on the same bus. But on something like an Arduino, how many I2C pins do I have? Do I just have one bus for the entire chip? Do I have multiple buses?
It depends on the Arduino. So, and the Arduino depends on the microcontroller. So if you look at, let's say, an 8-bit AVR Atmel version of an Arduino, like an Arduino Uno, I think it only has one I2C bus. So you can only have one physical connection to one or more I2C chips. And let's come back to that thought in a second. Some of the fancier chips, like the ARM-based processors, like an STM32, those, I don't know how many it has off the top of my head, but they might have 2 or 4 I2C buses. Now, does it really matter? For most of our applications, generally it does not matter. And the reason I say that is because I2C is what's called a multi-drop bus. So you can hook multiple peripheral chips onto that bus. So it's not a master-slave relationship. It's not a microcontroller to peripheral chip on these wires and we're done.
It sounds more like a network.
It is. It's kind of it's a bus. So they don't really it's not really a network. I mean, conceptually, it's kind of the same thing. But the idea is that let's say you had 2 memory chips because you want twice the memory capacity. And maybe you also want a magnetometer, like in our example. And you also want to have a temperature and humidity sensor. Well, the same clock and data wires, those 2 pins that come off the microcontroller, would go to the clock and data pins of every one of those 4 or 5 I2C chips. And the reason why every chip is manufactured with an address is that when the microprocessor says to the bus, I want to talk to device number 40, then the memory chip wakes up and says, oh, that's me, and everybody else ignores it. So you can only be talking to one chip at a time, but of course that's fine for most applications. So that's called a multi-drop bus. And depending on the parts that you use, you can go up to about 32 components on a bus. And it just depends on the load capacitance and the drive capacity of the devices. But in reality, you're probably going to put 1 or 2 or 3 parts on the bus, and that how many do you need for an application? Not that many. So you can have a mix and match of different parts from different vendors because they all follow the same bus protocol and electrical signaling standards. And to your point about those little jumpers, most of the I2C parts usually have typically 3 address pins and 2 to the third. So you have 8 possible addresses for your part. So when I say that the part is manufactured pre-coded as address number 40, those jumpers allow that part to be number 40, 41, 42, 43, 44, depending on where those jumpers are. So that way you can have half a dozen of that same kind of part, as well as other parts that have completely different address ranges. So you can imagine there's some coordination in the industry required to make sure that people don't make parts with the same address scheme. Yeah,
which is similar to in computer networking, there are MAC addresses, right? So you don't have the same hardware addresses happening across multiple manufacturers.
Same with USB identifiers in the HID elaborator. So you don't have, every USB device manufacturer has a code.
So, we've kind of talked in depth about this as a bus. And like you said, it's bidirectional, right? The main device, the microcontroller, can talk to the thing can talk back to the microcontroller. Some of the, I guess, the practical applications of this really are in a lot of the breakout boards that you will see from somebody like Adafruit or SparkFun are going to be I2C devices. And I mentioned light sensors, but there are sensors designed to help you detect if there is like carbon dioxide, carbon monoxide, oxygen, natural gas. I mean, there's all kinds of gas sensors out there. There are, of course, pretty common like temperature sensors and humidity sensors. There are sensors that will detect like sound pressure levels. There are sensors that will give you inertial measurements, like with, we talk about accelerometers, that they can give you motion data in three-dimensional space. There are just a lot of different sensors out there that are available either directly or on breakout boards that allow you to, really interact with the physical world.
Tons. In fact, we talked about the ADCs that are built into these microcontrollers, and they're typically 10 or 12-bit ADCs, which is the resolution. If you said, well, that's all fine, but I want a very precise voltage measurement, you can buy a breakout board that has a ADC that's 24 bits. That's so super high resolution. And guess what they use to communicate back to the microcontroller? I2C. So if you blow out of the resolution of that part of your micro, then use an outboard one. You could even use I2C, by the way, to communicate between microcontrollers. It's not done very often, but it has been done often, sometimes. So there's just lots of applications for that. So that's like really, really common, and frankly makes the physical board design way, way, way easier, because you don't have a bunch of routing trace congestion on your circuit board, and it's just easy to have a bunch of parts all laced together on those two wires.
So that's kind of, we've gone in depth on I2C and an introduction to serial buses. I'm aware that there are two more common serial interfaces. Yeah,
the other second most common is called SPI. SPI bus is the same concept as I2C, with kind of two basic differences. So the I2C bus is physically very simple. It's two wires, and it relies on some clever software in the micro and in the end device to be able to extract the data off the bus. The SPI interface is a little bit different in that it has more wires. So there is a clock, and instead of just a bidirectional data pin, you have a data output pin from the micro to the device, and a data input pin from the device back to the micro. So you could be sending and receiving data at the same time. There's also a chip select line where the peripheral device you're talking to has pin number 4 is chip select, and in order for that chip to respond, it doesn't have an address. It looks at when its chip select line is pulled low, typically. So you have to have a 4th wire. So to hook up just one peripheral chip to a microcontroller with SPI, you need at least 4, sometimes 5 wires to make that work. So, okay, it's more wires. The other difference is that SPI is, unlike I2C, it's not a multi-drop bus, which means that if I have 2 or 3 SPI devices, at a minimum, I have to have at least a chip select pin for every device. So you can see with SPI that the more chips I have, I start to burn up more and more pins on my microcontroller. Now, in a lot of applications, that's no big deal because, well, if you have 3 peripheral chips, maybe you're going to use 8 pins. That's not a big deal. Typically, there's plenty left over. So, okay, not so bad. The advantage of SPI is that...
let me ask you a question about that.
Yeah.
So, we talked about the input and output lines, right?
Right.
So if you had 3 hypothetical devices, are they all wired to those same like physically, like all the inputs are wired together, all the outputs are wired together. It's just that the device doesn't do anything unless its chip select line is hit.
Not exactly. So what you can do is, for instance, you can have the output pin from the microcontroller that goes to the peripheral chip. You could take that wire to all the peripheral chips and bus the output together to all the inputs. And the chip select line, only one chip select line will be active at a time, so only one chip will pay attention. But when the peripheral chips talk back to the microcontroller, that's where there's kind of a problem. So some SPI devices, you cannot bus the outputs together, and some you can. So it sort of depends on the chip.
Oh, so in some cases, you could literally have to tie up all those lines just to one thing.
Yeah, it winds up being like half, because you can use the same clock. The clock line, so the two outputs to the peripherals are the clock and the data. Those could be bused to all the SPI parts. The chip select line is unique to every part, and whenever I've done something with SPI, I've only ever talked to one part, so I've never really had this problem. When I do multiple chip things, it typically tends to be I2C. The advantage of SPI is you can get higher clock rates. You can get faster data throughput. So applications where there's a lot of data constantly going back and forth between the micro to the peripheral chip tends to be SPI. Applications where there's fewer transactions with the chip and there's less data being sent tends to be more I2C.
No, I mean, when you're talking about data speeds, like how fast, like what are the differences?
Well, that's a great question. So if you look at SPI, the original I2C spec, the clock rate on I2C standard is either 100 kilohertz or 400 kilohertz. There are many manufacturers which went beyond the industry standard speeds of 100 and 400 kilohertz, and you can find 1 megabit per second I2C parts, but not all the microcontrollers can handle it, so it kind of depends. With SPI, I know you can go faster. I'm not sure what the high-end speeds are, off the top of my head.
I have to imagine it's pretty fast, because I'm aware that there are SPI Ethernet chips available.
Right, that's correct. So it is faster. And I do think that most of these chips will allow you to bus the peripheral chip outputs together. So what that really means is that for SPI, for connections, you need clock, data in, data out, and as many chip selects as you have chips. So if you have 5 chips, you're going to need 1, 2, 3, 8 pins. With I2C, you only need 2. I think Ethernet's a great example. I've never seen an Ethernet to I2C interface chip, but I have SPI. So for really high-speed applications, then SPI is going to be superior.
Okay, so that covers I2C and SPI. Yeah. That leaves only the lowly UART.
Oh, yes, the lowly UART. Well,
what is the lowly UART?
Well, the UART, goes back to ancient Rome. So the UART, we talked about RS-232 and old-fashioned serial communications, the big DB9 connector and talking like your dumb terminal kind of ASCII sort of stuff. The chip on the inside of the computer that handled that serial deserializing is called a UART, and a UART is a universal asynchronous receiver transmitter, which is essentially a device that it's a parallel to serial converter. So it takes a parallel input from the microcontroller. This is all inside the chip, and converts it into a pattern of ones and zeros that get shipped out. So in practical sense, what the UART is you can send ASCII or binary data over it. It's asynchronous, meaning there's no synchronous clock line. Unlike I2C and SPI, they have clock signals. In RS-232 or the TTL logic signaling version of this, every character is its own separate little packet of data with its own little start bit, its data, to comprise the bits of the character and its own stop bit. And so you can send, type an A and it sends an A, then a B and it sends a B. So those are all independent little tiny packets. Now, the UART's been around forever, and every microcontroller has UARTs on it. And why? With all these fancy schmancy newer things, why would you have UARTs? And the answer is, it's kind of like the lowest common denominator. If you go out and buy like a GPS receiver, for instance, they'll have a UART as the interface, and you could hook your microcontroller to your GPS chip. So it's not the fastest, it's not the most efficient, it's not the smartest kind of an interface, but it is certainly the most ubiquitous.
Yeah, so I mean, when we're connecting like a KX3 over a serial cable or a USB to serial adapter to our computer, that's a UART interface.
Yeah, that's right.
And you mentioned RS-232, which the spec had very specific voltage requirements, but it has been my experience that you can have different voltaged, that's probably not a word, you can have UARTs running at different voltages.
Well, no, the UART really runs at whatever voltage the UART's designed to run at. You might have a level shifter on.
No. Sorry, that's what I mean. In other words, when you hear UART does not imply voltage. It's whatever the voltage of the architecture of the device is. Yeah,
exactly. So like on a microcontroller, on the Arduino, the UART, and there is one on an Arduino, is going to be 5 volts, 0 to 5 volts. So a logic 1 is 5, logic 0 is 0. If you were going to hook that up to a traditional RS-232 circuit, where the signaling is a plus and minus voltage, plus being a range from 5 to 15 volts-ish, and a 0 being a range of minus 5 to minus 15, reference to ground, you have to have a level shifter chip in between that converts that single-ended 0 to 5 to the plus and minus 15. So that's a whole chip by itself. That's like the MAX 232 chip that we talked about before.
Gotcha.
Now, the advantage of UART and serial data like that is it's totally everywhere. You can have an interface on a PC. You can have little data radios with UARTs. Every microcontroller has one. They're just super common. The downside...
Go ahead.
The downside is it's relatively slow compared to the other ones, the other serial interfaces, and it's only point-to-point. A UART normally, physically, talks from one thing to one other thing, and it's generally like a box of some box electronics to some other box electronics. Go ahead.
Well, you said what I was going to say is that generally UARTs are synonymous with being slower. I mean, anytime you've plugged into your radio or you have plugged into, if you have a Raspberry Pi, I was always a big fan of using the UART pins directly, which you had power and ground and then send and receive, as the 4 lines. But I mean, you're hooking up to it at like 115 kilobaud maybe at maximum. If it's your radio, it's going to be 9600 baud. It's not very quick at all compared to these other interfaces.
That's right. And there's nothing clever about it. Like I2C is clever because I can hang multiple parts off that bus. Each one has an address, etc. SPI is faster. It's probably in the megabits per second range at least. And UART is just dumb.
So just as an aside, I just searched because you made the comment you've never seen an I2C Ethernet interface. There's actually somebody who manufactures an Ethernet interface that can either be running at RS-232 TTL up to 4 megabit, I2C up to 2.8 megabit, which I was actually kind of surprised that the UART is faster there, and SPI up to 8 megabit for this particular breakout board. And this is kind of this is a prototyping tool that if you just need Ethernet for whatever it is that you're doing, this gives you the opportunity to do that.
Interesting. Yeah, I mean these interfaces are industry standards, and zillions of companies make parts, and sometimes they'll have proprietary versions that stretch the specs. You just never know. For the most part, we kind of stay in the lane. You know, we kind of use standard parts and standard speeds and standard stuff because that's kind of what's reliable and easy to get your hands on and easy to make work, and not really pushing the envelope a whole bunch. There is a fourth serial bus, by the way, that I should mention, and that's called OneWire. And
yeah, I've heard of that.
OneWire is a little bit of the red-haired stepchild because OneWire, like I mentioned, I2C was invented by Philips, but they put it in the public domain so everybody can make an I2C chip. I don't know if Philips actually gets royalties on that, but anyway, OneWire was invented by a company called Dallas Semiconductor, which was bought by Maxim Semiconductor some years ago. So they tried to make that kind of an industry standard. And as far as I know, I don't know anybody besides Maxim that makes OneWire compatible parts. Maybe somebody does, but it's mostly their own protocol for their own chips. And usually that's something that you would avoid, except for the fact that Maxim makes some really great chips, and they make some super popular chips as well. And one of the most popular chips they make is a temperature sensor. It's a digital temperature chip called an 18B20. And the 18B20 is the size of a TO92 transistor package. That's this little plastic transistor, 3-leaded device. And inside that little 3-leaded plastic package is a temperature sensor and a microcontroller that will convert that temperature into a number and will transmit that number serially over the pins of the temperature sensor.
Yeah, we talked about this during the Idiot Switch.
Oh, that's right. That's right. That was my suggestion of putting it by the tip. Yeah. So the advantage of OneWire, there's several actually, but one advantage of OneWire is that the length of the physical wire could be very long. So in I2C was intended to talk from one integrated circuit to another integrated circuit across a circuit board. It's not designed to talk on wires going across the room. It's not a network. OneWire was designed to send data over wires over fairly long distances. Like they're used widely in temperature sensors for buildings, where you're going to take a twisted pair of wires, run it across the floor, and drop temperature sensors off of it every 20 feet. So you can go for a pretty long way with OneWire. And anyway, it's not that hard to use. It's kind of like I2C from a software perspective, but it is its own separate protocol. And they do make a bunch of other chips that support OneWire, but that temperature thing is like super common. It's very popular. In fact, we use that in our repeater system monitoring thing that I talked about installing up at our repeater site. So we use these temperature sensors in little metal cylinders and about a 6-foot cable that runs to the controller, and they monitor the PA temperature.
I guess I mean, how common is that going to be on like the project boards?
Very common. It's surprisingly common. Actually,
does it have another name?
18B20. You'll find them all day. DS 18B20.
Okay.
Yeah, they're super duper common.
It's just when I look at like the pinouts of an Arduino Uno, I didn't see.
Oh, so actually, there's well, this brings up a sort of a tangent here, which is
well, we would never do that, George. Just cut that right out.
Okay, here's an hour deep dive on an irrelevant topic. Oh wait, that's an episode. So when you think about the pins of a microcontroller being for a particular purpose, sometimes for some of these serial interfaces, there is a piece of hardware in the chip that handles that protocol. And that's why only like this one pin is the I2C clock and this one pin is the I2C data, because inside the chip, the hardware to do that is behind those two pins and not somewhere else. There are other times when you can emulate the protocol not in hardware but in software. And there's pros and cons. If I could emulate the behavior of that I2C circuit in software, I could put that software behind any pin. And it's just a digital input and a digital output with all of the protocol handling done in software. The problem with that is that it's difficult to do high-speed communications or anything interrupt-driven in software. It's really only practical to do it in hardware. So if you want to do I2C properly, you really need to use hardware, and it has its hardware accelerator support in the chip. OneWire is implemented in software on every processor I've seen. So if you look at an Arduino, or you look at like an Atmel, or you look at a PIC, there's no one-wire pin. Any pin that's a digital I/O pin could be a one-wire pin because the one-wire protocol is all done in software. Now, the reason that they do it in software, or one of the downsides, is that it's kind of not very fast. Because in an application like give me the temperature, you're not trying to get the temperature a million times a second. You'd be happy with getting the temperature once a second. I mean, realistically, you need it once every 5 minutes.
Once every 5 minutes, yeah.
But maybe in some crazy applications you want to monitor it like 10 times a second, and OneWire will handle that. But it's not going to handle it a million times a second. So, like if you're trying to transport Ethernet traffic over that serial bus, forget it. Because, at 1 megabit per second, you need a lot of clock cycles. So there's no way OneWire can handle Ethernet. But
Gotcha.
SPI could.
Gotcha.
But to do SPI, you're not going to do the SPI driver all in software. You're going to put it on the SPI pins, because behind the SPI pins is a piece of hardware which implements the protocol in hardware so it can handle it fast enough. You wouldn't be able to do it in software unless you had a super duper fast computer.
Okay. So I think that covers pretty much all the specialized serial pin interfaces. And of course, again, those are used mostly for interfacing with devices that have some level of intelligence. It's not just reading an analog sensor and getting a voltage level out of it, which, actually, I should say this is probably obvious, but it wasn't obvious to me until I really had an oscilloscope. I never realized that, signal is voltage, and varying the voltage is varying your signal. Again, that is probably obvious to every human being but me. But
you got it.
I've got it now, yeah. But one of the things that is kind of cool is to sit down if you have an oscilloscope. I like the analog discovery we've talked about. There are other, like computer-based ones or hardware. If you bought the Regal we recommended, but it's kind of cool to just put these things down and load sketches and have them interact with things and probe around to get a really good physical representation. In fact, talking about the serial bus thing, oftentimes it is helpful to see what's happening on these buses, and this is where a device called a logic analyzer comes in. Mm-hmm. And a logic analyzer is basically a digital probe that will, you clip on to wherever you need to clip on, depending on the number of connections and whatnot. And there is either in hardware or in software, it captures the signals that it sees and then does translation. So like in the Regal oscilloscopes, like the 1000Z series, the 2000, the 4000, 6000, all of them have options to have either hardware logic analyzers where there are actually boards doing it, or they can do it in software where the scope records the data and then it's parsed by their software to decode it. I actually, for logic analysis, prefer PC-based tools because you can scroll and do things with a mouse, copy and paste. George, again, we've talked about the Analog Discovery 2 at great length, but that is a logic analyzer. Now, that's one of the features, and then a protocol decoder for I2C, SPI, and UART. There's another company out there called, I think it's Saleae, Saleae. I think you pronounce it Saleae. The logic analyzer that I own is one that they make that is, I think 8-channel or 16-channel. I can't remember. They make both. I think mine's 8. But it's really cool because if I wanted to see what's happening, like if I'm not getting an expected result from a device, I can use this to actually read what's happening over the bus to try to troubleshoot and, see, is my data getting messed up somewhere along the line, or am I misinterpreting what I'm reading, etc.
Yeah, that could be really handy. If you do a lot of these serial bus projects and you're running into problems, that's super helpful. I've been pretty lucky that I haven't resorted to that much at all. pretty much I do all my debugging in software, and I really haven't had to go scope the bus and look at the data. But even if you don't have to, it is really interesting just to look at it and see what's actually sent back and forth.
Yeah, I mean, and I'm a very visual learner. I have learned a lot by having the ability to see what's going on. Like I remember when I first got the Logic Analyzer, I hooked it up to a GPS receiver that just spits out UART NMEA data. Mm-hmm. And it was just really interesting to see, what do the pulses look like to form an ASCII character?
Right.
And with UARTs, if anybody's ever played around with serial, the most common serial port configuration on a computer is, we would say, baud rate and then 8N1, right? Which is 8 bits, non-parity, and I forget what the 1 means.
One stop bit,
yeah. So that kind of describes how are the electrical signals going to be configured to transmit data. And obviously for quote-unquote serial over a UART, there are options. But it was just very helpful for me to actually see, those square waves pop up. And it's like when you hit A, like you said, you see 8 bits come through. And that's really cool.
Yeah, I think that's a wonderful training and learning step to see the physical thing, because then I really do see what's physically going on here, and it's not just all abstracted away. And I think as hams, we kind of like hardware stuff in general. I mean, much as we talk about software, it's interesting to see how the hardware things actually really do work.
And that's, here recently, I myself, I know you picked up an analog discovery. I myself have had great interest in one here recently. And I mean, if you don't have any of this higher level test equipment, you don't have an oscilloscope. I mean, it really is an immense amount of power in a small portable package that's not that expensive, that allows you to have, to literally see the magic happening, which is a little bit of hyperbole. But I mean, that's how I feel. Like when I see waveforms on a screen, like I'm just like, wow, that's how that cool thing is happening.
Well, and if something doesn't work and you have that visibility, you can look at that and at least understand if the waveforms appear clean or not, or are they even coming out at all? I mean, if you are talking to a chip and you're sending an I2C packet and you're not getting any response, well, is it because you're sending the wrong data? Is it because it's physically not coming out of the chip? If it's physically coming out of the chip, is it garbled up or is it correct? So, you when you start debugging stuff, you have to start like lifting the lid and looking at the stuff and, start to eliminate things that seem to be working properly to figure out what the heck's wrong.
All right. Well, I think that's going to about wrap up the topic of interfacing with stuff.
Yeah, that's pretty much it for physical interfacing. I think the one other topic we could get to at some point is there are some other communications interfaces like RF data radios and RS-485 and other stuff like that, which is often used in this world as well. But perhaps that would be good to dive into in a different episode.
I think it would be. What would be really awesome is if we talked about LoRa ham as a project, I think last time. Mm-hmm. LoRa is a radio data communication standard, and of course you interact with those devices using UARTs. It would be really cool if we could somehow get Travis Goodspeed to come on the show to talk about it.
Yeah, I'd love to talk to him about it, because I've been building projects with these kinds of things, not LoRa specifically, quite a bit. And in fact, our whole repeater site monitoring system is all 2.4 gig mesh network devices all hooked together. That's become very easy to do. I mean, that's not an esoteric thing. It's actually pretty simple. And it's an awesome capability. And LoRa it promises some capability for long range, low power data communications. And I would be very interested to see what he's doing with his project.
All right. Well, I think this is a pretty good primer. I mean, this topic applies to pretty much any of the types of, everything from a particle photon to an Arduino, Raspberry Pi, whatever the board du jour is. And again, we are starting to see things kind of change. because we're going from 8-bit microcontrollers, which are really inexpensive, and people have reached the limits of those, and now they want to start getting into 32-bit ARM-based microcontrollers. And of course, I say those words, and I don't necessarily understand what that means. But I think a couple of good topics coming up will be kind of a deeper dive on the plethora of microcontrollers available today and kind of comparing them. And then start talking about how do you interface them. It's like, that's great that you have something that's talking or observing or interacting with the physical world. But then how do I take that data and actually do something with it in a larger context? How do I get it access to it from a distance, either through a direct radio link or through the internet?
Yeah, exactly. And then you also start to get into the software side of those things too. So if it goes to the internet, what kind of software do I need to access that? Do I build some kind of web service or what to actually be able to see that and interact with that data?
So maybe our next episode we'll kind of talk about the different architectures of these chips, and then get into this kind of wide area communication, and then maybe top it all off. I personally would be very interested to deep dive on all of the repeater site control and monitoring stuff that you guys have done, because I mean, at the end of the day, that's the practical application for this knowledge. Plus, we've gone a little bit heavy on the electronic side. That would definitely bring us back to our ham roots.
Yeah, I think that would be a good example, because it uses every technique that we talked about in this show about using analog to digital converters to measure voltages and currents and logic states and controlling relays and reading RF power, which we didn't talk about in the show, but again, uses ADCs. These data radios, everything we've talked about here came together in that site monitoring project. And whether you're a repeater owner, or maybe you want to do a remotely controlled station at home, or maybe you just want to monitor something at home, that could be a good example of how we approach that problem and what we built, and some of the trade-offs, and how you could do it yourself.
Awesome. Well, I want to personally thank everybody for continuing to come along this journey as we're kind of deep diving on these topics. As always, you can get in touch with us by sending an email to workbench@hamradio360.com. And then you can find me spending most of my time on Twitter at KF7IJZ.
And I'm George at hamradio360.com or at KJ6VU on Twitter.
And don't forget, the time is running out on the 10% off coupon for MCM Electronics at mcmelectronics.com. That coupon code again is RAD10, and that is good until the 31st of January.
And we'd also like to suggest, if anybody has questions to put at the end of the show, or if you have any questions for our sponsors too, we can get them on board here and chat about some of their products and things they do. And we're looking forward to some of those things in the coming months in this new year. So thanks a lot, and have a great week.
Well, we did get one question, but I'm not going to dignify it with a response.
What question was that?
It was from this loser whose call sign is K4CDN. He was harassing. Oh, you really didn't see this?
No.
Oh, he asked he asked us who our favorite Ham Radio 360 host was.
Oh, that's easy. Jeremy.
George.
Yeah. Not that other guy.
No, that other guy. No.
Hey, by the way, that other guy had a great show last week. It had Stuart on the show talking about. Stuart is like our man in the national parks on the air. He did like 1 million contacts. I don't know what he did, but it was unreal. So that was awesome, and it was really a fun show.
Indeed, it was.
All right, till next time.
Thanks for listening. 73. Let's get this show on the road, shall we?
Let's do.
Well, hold on. Do you want to start us?
No, you do it.
Okay. Oh, sweet. We're back.